Look up at the night sky and you witness one of the universe's most profound mysteries. Stars hang suspended in the cosmic void, planets trace their eternal paths, and somewhere above your head, the International Space Station circles Earth at 17,500 miles per hour. Yet none of this celestial choreography falls down. Why? This question has haunted humanity for millennia, driving some of our greatest minds to the very edge of understanding. The answer, as we shall discover, lies not in some invisible force reaching across the emptiness of space, but in the very fabric of reality itself. Gravity, it turns out, is not what we thought it was. To understand this revolutionary idea, we must first journey back to ancient Greece, where a brilliant philosopher named Aristotle gazed at the same stars and formulated ideas about motion that would dominate human thinking for nearly 2,000 years. Born in 384 BCE in the Macedonian town of Stagira, Aristotle possessed one of history's most penetrating intellects. He studied under Plato for 20 years, tutored the young Alexander the Great, and founded his own school, the Lyceum, where he would develop a comprehensive theory of the natural world. In Aristotle's cosmos, everything had its ordained place in a grand hierarchy of existence. Earth, being heavy, dense, and imperfect, belonged at the very center of the universe. This wasn't arbitrary placement, it was cosmic necessity. Water, lighter than Earth but heavier than air, naturally settled in a sphere surrounding the solid ground. Air, lighter still, formed the next layer outward. Fire, the lightest of the terrestrial elements, rose naturally toward the heavens, seeking its proper realm above the atmosphere. Beyond these four earthly elements lay something entirely different, the celestial realm. Here, perfect crystalline spheres made of a fifth element called quintessence rotated in eternal, unchanging circles. The moon occupied the innermost celestial sphere, followed by Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond them all lay the sphere of fixed stars, and beyond that, the prime mover, the source of all cosmic motion. According to Aristotelian physics, objects fell toward Earth not because of any external force, but because they were seeking their natural place in this cosmic hierarchy. A stone dropped from your hand didn't fall because something was pulling it downward. It fell because stone, being earthy in nature, belonged with earth at the center of everything. The heavier an object, the more earthy material it contained, and therefore the more eagerly it sought to return to its natural home. This explained why a brick falls faster than a feather. The brick, dense with earthy matter, possessed a stronger desire to reach the center. The feather, containing more air than earth, fell more slowly because it was less eager to leave its natural realm. Everything made perfect sense within this framework. Medieval scholars embraced Aristotle's teachings with enthusiasm, weaving them into an even grander cosmological tapestry. Islamic philosophers like Averroes and Avicenna refined Aristotelian thought, while Christian thinkers like Thomas Aquinas integrated it with theological doctrine. In their vision, Earth sat motionless at the center of concentric crystalline spheres, each one transparent and perfect. Angels pushed the planets along their circular tracks, their divine influence maintaining the eternal celestial dance. The spheres themselves produced celestial music as they rotated, a harmony of the heavens that permeated all creation. This worldview satisfied inquiring minds for centuries. It was elegant, comprehensive, and seemed to match everyday experience. After all, doesn't a brick fall faster than a feather when you drop them? Don't heavy objects naturally seek the ground while flames leap skyward? The system explained not just falling objects, but the entire structure of the cosmos, from the humblest pebble to the most distant star. But then came Galileo Galilei. a man whose insatiable curiosity would shatter this ancient worldview like a hammer striking stained glass. Picture the scene: Pisa, Italy, sometime around 1590. A 36-year-old mathematics professor named Galileo Galilei climbs the 294 steps of the famous Leaning Tower, his footsteps echoing in the marble spiral staircase. In his hands, he carries two metal balls, one significantly heavier than the other. Word has spread through the university that the professor plans to challenge Aristotle himself, and a small crowd has gathered in the piazza below. The people of Pisa know their Aristotle well. Heavy objects fall faster than light ones because they contain more earthy matter, more desire to reach their natural place at the center of the world. This isn't mere theory, it's observable fact. Everyone has seen stones outrace leaves to the ground, coins fall faster than pieces of paper. What could this young professor possibly hope to prove? Galileo reaches the top of the tower and peers down at the gathered faces, some curious, others skeptical, a few openly hostile. The wind off the Arno River ruffles his beard as he holds the two spheres aloft, one in each hand. According to Aristotle, according to 2 millennia of accepted wisdom, the heavier ball should strike the ground first, arriving well before its lighter companion. But when Galileo releases them simultaneously, something extraordinary happens. The balls fall together side by side, their descent perfectly synchronized. They strike the cobblestones at precisely the same instant, the sharp crack echoing off the surrounding buildings like a gunshot. The crowd falls silent. In that moment, watching two metal spheres lie motionless on ancient stones, 2,000 years of accepted wisdom begins to crumble. But Galileo's most important work happened not atop dramatic towers, but in the quiet confines of his laboratory. Using inclined planes of his own design, he rolled bronze balls down smooth wooden ramps, timing their motion with water clocks and the steady rhythm of his own pulse. What he discovered revolutionized our understanding of motion itself. Objects in freefall, Galileo found, accelerate uniformly. Every second, a falling object gains approximately 32 feet per second of speed, regardless of its weight. A cannonball and a musket ball, dropped from the same height, will hit the ground at the same moment. A feather falls slower than a stone only because the air around them offers resistance. Remove the air, create a vacuum, and feather and stone fall together in perfect unison. This was earth-shattering insight. Galileo had discovered that motion follows mathematical laws, precise and predictable, not the vague philosophical tendencies that Aristotle had proposed. Objects don't fall because they're homesick for the center of the world. They fall because they're being uniformly accelerated by something acting upon them. But what was that something? Galileo also turned his telescope skyward, becoming the first human to see the cosmos through magnified eyes. He discovered mountains on the moon, destroying the notion of perfect celestial spheres. He found 4 moons orbiting Jupiter, proving that not everything in the heavens circles Earth. He observed the phases of Venus, confirming that planets orbit the Sun, not our world. Each discovery chipped away at the Aristotelian cosmos, replacing supernatural explanations with mathematical precision. Yet even Galileo couldn't answer the fundamental question: what causes objects to fall in the first place? That answer would come from an unlikely source: a 23-year-old Cambridge student named Isaac Newton, sitting in his mother's garden during the plague year of 1666. As legend tells it, Newton was contemplating the motion of the moon when an apple fell from a tree nearby. But rather than simply noting the apple's descent, Newton's extraordinary mind made a connection that would transform our understanding of the universe. What if, he wondered, the same influence that pulls the apple earthward also holds the moon in its orbit around Earth? This was a breathtaking leap of imagination. Since ancient times, The terrestrial realm of falling apples and the celestial realm of orbiting moons had been considered completely separate domains, governed by entirely different principles. Earthly objects fell in straight lines toward the center, while celestial objects moved in perfect circles forever. How could they possibly be connected? But Newton dared to think they might be unified by a single universal principle. Working feverishly through the plague years, while Cambridge University remained closed and he lived in isolation at his family's manor in Woolsthorpe, Newton developed his revolutionary law of universal gravitation. Every particle of matter in the universe, Newton declared, attracts every other particle with a force that depends on just two things: how much matter each particle contains and how far apart they are. Double the mass of either particle and you double the gravitational force between them. Double the distance between them and the force becomes 4 times weaker. Triple the distance and it becomes 9 times weaker. The mathematical relationship was elegant in its simplicity. Force equals the gravitational constant times the product of the two masses, divided by the square of the distance between them. Newton's law was breathtakingly successful. It explained why planets follow elliptical orbits rather than perfect circles, something that had puzzled astronomers for centuries. It predicted the timing of ocean tides with remarkable accuracy, showing how the moon's gravity tugs at Earth's waters as our planet rotates beneath it. It explained why Earth bulges slightly at its equator, flattened by its own rotation against the inward pull of gravity. Using Newton's law, astronomers could predict the return of comets decades in advance. They could calculate the masses of planets by observing their moons and determine the mass of the Sun by measuring Earth's orbital period. When the planet Uranus showed slight deviations from its predicted orbit, astronomers used Newton's law to calculate that another, more distant planet must be pulling on it. They pointed their telescopes at the predicted location and discovered Neptune, a triumph of mathematical physics over pure observation. For the first time in human history, the cosmos had become predictable. The wandering stars were no longer mysterious lights pushed by angels. They were massive worlds following precise mathematical paths through space. The universe operated like clockwork, its every motion governed by Newton's elegant equations. But Newton's gravity came with a deeply troubling mystery that would haunt physics for the next 2.5 centuries. How could this gravitational force reach across the vast emptiness of space to influence distant objects instantaneously? The Sun somehow reaches across 93 million miles of perfect vacuum to keep Earth in its orbit. Earth reaches up 240,000 miles through empty space to tug on the Moon and raise the tides. Jupiter, 500 million miles away, still exerts enough gravitational influence to deflect passing comets. How is this possible? Newton himself was profoundly uncomfortable with this action at a distance. In his masterwork, the Principia Mathematica, he wrote with unusual humility, "I have not yet been able to discover the cause of these properties of gravity from phenomena, and I frame no hypotheses." He could describe gravity's effects with mathematical perfection, calculating planetary orbits to extraordinary precision. But he couldn't explain the mechanism by which it worked. Imagine trying to push a bowling ball across a room without touching it, without any rope or stick or lever or intermediary object of any kind. You simply point at the ball and somehow, mysteriously, it begins to roll toward you. Impossible, right? Yet Newton's gravity seemed to do exactly this on a cosmic scale. Massive objects reached across millions of miles of empty space to influence each other through pure nothingness, with no apparent means of transmission. Some of Newton's contemporaries proposed elaborate solutions to this puzzle. Perhaps space was filled with an invisible medium, an ether that could transmit gravitational influence like ripples spreading across a pond. Others suggested that tiny particles might constantly stream between massive objects, somehow creating the illusion of attraction through impact. Still others wondered if God himself might directly guide every falling apple and orbiting planet. His divine will manifesting as what we perceive as gravitational force. But none of these explanations could match the mathematical precision of Newton's law, and most created more problems than they solved. The ether, if it existed, would have to be completely invisible, yet strong enough to transmit the enormous forces holding planets in orbit. Streaming particles would gradually slow down the planets they were meant to guide. Divine intervention, while perhaps theologically satisfying, removed the question from the realm of natural philosophy entirely. For 2.5 centuries, scientists and philosophers lived with this fundamental paradox. Newton's law of gravitation worked magnificently for practical purposes. Engineers used it to design artillery trajectories and predict cannonball flights. Astronomers used it to chart the courses of comets and discover new planets. Eventually, rocket scientists would use it to launch spacecraft to the moon and beyond. Yet the central question remained stubbornly unanswered. How does gravity actually work? The breakthrough would come from an entirely unexpected direction. A young patent clerk in Bern, Switzerland, who spent his spare time thinking about seemingly unrelated questions involving light, motion, and the fundamental nature of space and time themselves. Albert Einstein, working alone in his small apartment above the streets of the Swiss capital, would soon discover that Newton's mysterious action at a distance was based on a fundamental misunderstanding about the very arena in which cosmic drama unfolds. Space and time, Einstein would reveal, are not the separate, absolute, unchanging backdrop that Newton had assumed. They are woven together into a single, dynamic fabric that can bend, stretch, curve, and even ripple like the surface of a disturbed pond. Gravity is not a mysterious force reaching across this fabric to pull distant objects together. Gravity is the fabric itself, warped and curved by the presence of matter and energy. Mass and energy don't reach across empty space to tug on distant objects. Instead, they bend and distort the very geometry of space and time around them, creating curves and valleys and hills in the fabric of reality itself. Objects then follow the straightest possible paths through this curved space-time, paths that appear to us as the elliptical orbits of planets, the parabolic trajectories of thrown balls, and the straight downward plunge of falling apples. But to understand this revolutionary insight, we must first grasp Einstein's earlier discovery about the nature of space and time themselves. We must learn how these seemingly separate and absolute quantities are actually aspects of a single flexible reality that Einstein called spacetime. The year was 1905, and the world stood on the threshold of a revolution that would shatter humanity's most basic assumptions about reality itself. In the patent office of Bern, Switzerland, a 26-year-old clerk named Albert Einstein was about to publish a paper that would fundamentally alter our understanding of space, time, and the very fabric of existence. Einstein had been wrestling with a profound puzzle that had emerged from the work of 19th century physicists. Light, they had discovered, behaves like a wave, rippling through space, much as sound waves ripple through air or water waves cross the surface of a pond, but waves require a medium to travel through. Sound needs air or water or some material substance to carry its vibrations. Ocean waves need water. What medium carries light waves across the vacuum of space? The answer, according to the greatest minds of the 1800s, was the luminiferous ether, an invisible, massless substance that supposedly filled every cubic inch of the universe. This ether had to possess extraordinary properties. It needed to be rigid enough to transmit light waves at enormous speeds, yet so tenuous that planets could pass through it without resistance. It had to permeate everything, from the space between stars to the gaps between atoms in solid matter. But when experimenters tried to detect this ether, they found nothing. The most famous attempt was carried out by Albert Michelson and Edward Morley in 1887. They reasoned that as Earth moves through the ether in its orbit around the Sun, there should be an ether wind that affects the speed of light in different directions. Using an ingenious device called an interferometer, they measured the speed of light traveling parallel to Earth's motion through space and compared it to light traveling perpendicular to that motion. According to ether theory, light traveling with the ether wind should move faster than light traveling against it, just as a swimmer moves faster downstream than upstream. But Michelson and Morley found no difference at all. Light traveled at exactly the same speed in every direction, regardless of Earth's motion through space. The ether wind simply didn't exist. This null result sent shockwaves through the physics community. How could light waves propagate without a medium? Various scientists proposed increasingly desperate explanations. Perhaps Earth somehow drags the ether along as it orbits the Sun. Perhaps the ether exists but has properties so strange that it affects space and time themselves. Perhaps the measuring instruments contract in the direction of motion, hiding the ether's effects. Einstein approached the problem from an entirely different angle. What if, he wondered, the absence of an ether wind wasn't a failure to detect something that should be there? What if it was revealing a fundamental truth about the nature of light itself? In his special theory of relativity, published in 1905, Einstein made a startling proposal. Light doesn't need a medium because light defines the medium. The speed of light in a vacuum, approximately 186,000 miles per second, is not just another physical constant like the mass of an electron or the charge of a proton. It is the fundamental speed limit of the universe, the maximum rate at which any information or influence can travel from one point to another. But Einstein's insight went far deeper than simply explaining the Michelson-Morley experiment. If the speed of light is truly constant for all observers, regardless of their motion, then space and time themselves must be flexible, stretching and contracting to ensure that light always travels at the same speed. Consider this thought experiment. Imagine you're standing on a train platform, watching a high-speed train approach at half the speed of light. On board the train, a passenger turns on a flashlight, sending a beam of light forward toward the front of the train. From the passenger's perspective, the light beam travels away from the flashlight at the speed of light. But from your perspective on the platform, shouldn't the light be traveling at the speed of light plus half the speed of light since it's been launched from a moving train? In Newton's universe, this would indeed be the case. Velocities simply add together like numbers on a calculator. But Einstein realized that this can't be true, because the Michelson-Morley experiment proved that light always travels at the same speed for every observer. The light beam from the train's flashlight must somehow travel at exactly the speed of light from your perspective on the platform, even though it was emitted from a source moving at half that speed. The only way this can work is if space and time themselves adjust to make it happen. From your perspective on the platform, the train appears shorter than it would if it were at rest, contracted in the direction of its motion. Time on the train appears to run slower than time on the platform. The passenger's clocks tick more slowly, his heartbeat slows down, his thoughts proceed at a more leisurely pace. Space contracts and time dilates by exactly the amounts needed to ensure that light travels at the same speed for both of you. This isn't just theoretical speculation. These effects have been measured countless times with extraordinary precision. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground. Particles accelerated to high speeds in laboratory accelerators live longer than they should, their internal clocks slowed by their motion. GPS satellites orbiting Earth must constantly correct their clocks to account for the fact that time runs differently at their altitude and orbital speed. Einstein's special relativity revealed that space and time are not separate, absolute quantities as Newton had assumed. They are intimately connected, woven together into a single four-dimensional fabric that physicists call spacetime. An event doesn't happen at a particular place and a particular time. It happens at a particular location in space-time, defined by 3 spatial coordinates and 1 temporal coordinate. To visualize this concept, imagine a 2-dimensional creature living on the surface of a flat sheet of paper. This creature can move forward and backward, left and right, but has no concept of up and down. From its perspective, its world is purely 2-dimensional. But we, living in 3 dimensions, can see that the paper might be curved or twisted in ways the creature cannot perceive. Similarly, we live our daily lives thinking in terms of 3 spatial dimensions and 1 separate time dimension. But Einstein showed that these 4 dimensions are actually woven together into a single space-time fabric. And this fabric can be curved and distorted in ways that we don't normally perceive. The implications are profound. In Newton's universe, simultaneity was absolute. If 2 events happened at the same time, they happened at the same time for everyone, regardless of where they were or how fast they were moving. But in Einstein's space-time, simultaneity is relative. Events that appear simultaneous to one observer may appear to happen at different times to another observer, moving at a different speed. Consider 2 explosions that occur simultaneously on opposite ends of a moving train, as observed by a passenger in the middle of the train. The light from both explosions reaches the passenger at the same moment, confirming that they happened simultaneously from her perspective. But an observer standing on the platform outside sees something different. From his perspective, the train is moving forward, so the rear explosion's light has farther to travel to reach him than the front explosion's light. He sees the front explosion first, then the rear explosion, and concludes that they didn't happen simultaneously. Who is right? In Newton's universe, this would be a meaningful question with a definitive answer. But in Einstein's space-time, both observers are equally correct. Simultaneity is not a property of events themselves, but a relationship between events and observers. There is no universal now that extends across all of space. This relativity of simultaneity leads to some of the most mind-bending consequences of special relativity. If you could travel to a star 10 light years away at 99% of the speed of light, the journey would take about 10 years as measured by Earth-based observers. But your onboard clocks would show that only about 1.5 years had passed. You would age 1.5 years while Earth aged 10 years. This isn't science fiction. It's the inevitable consequence of the fact that space and time form a unified space-time fabric. Einstein also discovered that mass and energy are equivalent, related by his famous equation E equals mc squared. A small amount of mass can be converted into an enormous amount of energy because the speed of light squared is such a large number. This principle powers the stars, turning hydrogen into helium and releasing the energy that lights up the cosmos. It also revealed the terrible potential for both creation and destruction that lies hidden in the heart of every atom. But special relativity applied only to objects moving at constant speeds in straight lines. What about acceleration? What about gravity? These questions would lead Einstein to an even more revolutionary insight. Gravity itself is not a force, but a manifestation of the curvature of space-time. To understand this leap, consider what happens when you're in an elevator. If the elevator is at rest or moving at constant speed, you feel your normal weight pressing down on the floor. But if the elevator suddenly accelerates upward, you feel heavier, pressed more firmly against the floor. If it accelerates downward, you feel lighter. If the elevator cable snaps and the elevator goes into free fall, you feel weightless, floating freely inside the falling chamber. Einstein realized that there's no way to distinguish between the effects of gravity and the effects of acceleration without looking outside. A person in a windowless falling elevator feels exactly the same as an astronaut floating in deep space, far from any gravitational influence. A person in an elevator accelerating upward feels exactly the same as someone standing on the surface of a planet. This equivalence principle, as Einstein called it, suggested that gravity and acceleration are not just similar, they are identical. But how could this be? Acceleration involves changes in motion through space and time. If gravity is equivalent to acceleration, then gravity must somehow involve the geometry of spacetime itself. The answer would come from Einstein's general theory of relativity, published in 1915 after years of intense mathematical struggle. But to understand general relativity, we must first grasp how special relativity transformed our picture of space and time from separate, absolute entities into a unified, flexible spacetime fabric. In Newton's universe, space was like an enormous rigid container, a three-dimensional grid extending infinitely in all directions. Time was like a cosmic metronome, ticking away at the same rate everywhere, unaffected by the contents of space or the motion of objects within it. Matter moved through space as time marched forward, but space and time remained aloof and unchanging, the passive stage upon which cosmic drama unfolded. Einstein's spacetime is radically different. Space and time are woven together into a dynamic, flexible fabric that can stretch, compress, and curve. The presence of matter and energy affects the geometry of this fabric, and the geometry of the fabric affects the motion of matter and energy. Space and time are no longer passive observers of cosmic events. They are active participants. This transformation in our understanding of space and time set the stage for Einstein's next great insight. If space-time can be curved and distorted, then perhaps gravity is not a mysterious force acting across empty space, but the curvature of space-time itself. Mass and energy don't pull on distant objects through some invisible mechanism. They warp the fabric of reality, creating curves and valleys that guide the motion of everything from planets to photons. But working out the mathematics of curved spacetime would require Einstein to master entirely new areas of mathematics that had been developed by 19th century geometers studying abstract curved surfaces. The journey from special relativity to general relativity would take Einstein 10 years of intense struggle, grappling with concepts that challenged not just his understanding of physics, but his understanding of mathematics itself. The reward for this effort would be a theory of breathtaking beauty and power, one that would revolutionize our understanding of gravity, predict the existence of black holes and gravitational waves, explain the expansion of the universe, and provide the foundation for modern cosmology. General relativity would reveal that we don't live in Newton's clockwork universe of forces acting across rigid space and absolute time. We live in Einstein's dynamic cosmos, where matter and energy dance with the very fabric of space-time in an eternal cosmic choreography. Berlin, 1915. The Great War rages across Europe, tearing apart the fabric of civilization. Yet in a quiet study overlooking the Prussian capital, Albert Einstein makes a discovery that will transform humanity's understanding of the cosmos itself. After 8 years of mathematical struggle, wrestling with concepts that push the boundaries of human comprehension, he finally grasps the deepest secret of gravity. It is not a force at all. It is geometry made manifest. The journey to this revelation began with a simple observation that would have profound consequences. Einstein noticed something peculiar about gravitational acceleration. Unlike other forces, gravity affects all objects identically, regardless of their composition, size, or internal structure. A feather and a hammer, dropped simultaneously in a vacuum, fall at exactly the same rate. This universality seemed almost magical compared to other forces in nature. Consider electromagnetic forces. A charged particle responds to electric and magnetic fields based on its specific charge and mass. Different particles experience different accelerations in the same electromagnetic field, but gravity treats a grain of sand and a massive boulder with perfect equality, accelerating both at precisely 9.8 meters per second, squared at Earth's surface. This led Einstein to his principle of equivalence, a deceptively simple idea with revolutionary implications. Imagine being trapped inside a sealed chamber with no windows to the outside world. If someone asks whether you're experiencing the pull of gravity or the push of acceleration, there is absolutely no experiment you can perform within that chamber to determine the answer. The sensations are identical, indistinguishable, equivalent. This equivalence suggested something remarkable. If gravity and acceleration produce identical effects, perhaps they are not merely similar phenomena, but the same phenomenon viewed from different perspectives. But acceleration involves motion through space-time. If gravity is equivalent to acceleration, then gravity must somehow be woven into the very structure of space-time itself. Einstein's breakthrough came when he realized that this equivalence could be explained if massive objects actually curve the fabric of space-time. Imagine space-time as a vast, flexible membrane stretched taut across the universe. When you place a heavy bowling ball on a stretched rubber sheet, it creates a depression, a curvature in the sheet's surface. Now roll a marble across the sheet. Instead of traveling in a straight line, the marble curves around the depression, following the contours created by the bowling ball's presence. This is precisely how Einstein envisioned gravity working in space-time. Massive objects like stars and planets create curvatures, depressions, and warps in the four-dimensional fabric of space-time. Other objects, from tiny particles to massive galaxies, simply follow the straightest possible paths through this curved geometry. What we perceive as gravitational attraction is actually objects following geodesics, the shortest routes through curved space-time. This geometric interpretation explains the universality of gravitational acceleration. All objects follow geodesics through space-time regardless of their composition, because geodesics are properties of space-time geometry itself, not properties of the objects moving through it. A soap bubble and a cannonball follow identical paths because they're both taking the same geometric route through the same curved space-time. But translating this insight into precise mathematical form required Einstein to master tensor calculus, a branch of mathematics developed by Italian mathematician Gregorio Ricci Cabastro and his student Tullio Levi Civita for studying curved surfaces in arbitrary numbers of dimensions. Einstein called it an enormous labor, admitting that his mathematical training had not prepared him for such abstract concepts. Working with his friend and colleague Marcel Grossmann, Einstein spent years developing the mathematical machinery needed to describe curved spacetime. They needed equations that could relate the curvature of spacetime at each point to the distribution of matter and energy at that point. The mathematics was fearsome in its complexity, involving arrays of numbers called tensors that described how spacetime curves in response to the presence of mass and energy. The breakthrough came in November 1915, when Einstein finally wrote down his field equations. These 10 interlinked differential equations, compact enough to fit on a single line, yet containing the entire gravitational physics of the universe, describe how matter and energy determine spacetime curvature, and how space-time curvature determines the motion of matter and energy. The physicist John Wheeler later captured the essence of these equations in a memorable phrase: "Matter tells space-time how to curve, and curved space-time tells matter how to move." This reciprocal relationship between matter and geometry lies at the heart of general relativity. Mass and energy create curvature, curvature guides motion, and moving matter redistributes energy. creating new curvatures in an endless cosmic dance. Einstein's first triumph came when he applied his new theory to a long-standing puzzle in astronomy. The planet Mercury, closest to the Sun, follows an elliptical orbit that slowly rotates over time. The point of Mercury's closest approach to the Sun, called its perihelion, advances by about 574 arc-seconds per century. Newtonian mechanics could explain most of this precession as the result of gravitational tugs from other planets. But 43 arc-seconds per century remained mysteriously unaccounted for. When Einstein calculated Mercury's orbit using his curved space-time equations, the extra precession emerged automatically. The intense curvature of space-time near the Sun causes Mercury's orbital ellipse to rotate at exactly the observed rate. No mysterious forces, no undiscovered planets, no modifications to Newton's laws were needed. The anomalous precession was simply Mercury following its geodesic path through the curved space-time created by the Sun's enormous mass. This success convinced Einstein that his geometric theory of gravity was on the right track. But the real test would come from entirely new predictions that could be verified through observation. General relativity predicted that light itself should follow geodesics through curved space-time, meaning that light rays should bend when passing near massive objects. This bending occurs because photons, despite having no mass, carry energy and momentum. In curved space-time, the straightest possible path for a photon may appear curved to distant observers. The effect is tiny under normal circumstances, but becomes measurable near objects as massive as stars. Einstein calculated that light from a distant star, passing close to the edge of the Sun, should be deflected by 1.75 arc-seconds, about twice the deflection predicted by treating light as particles subject to Newtonian gravity. But measuring this deflection posed a seemingly impossible challenge. Stars are visible only at night, while the Sun's gravity can bend their light only during the day when the Sun itself outshines every star in the sky. The only solution was to observe stars during a total solar eclipse, when the Moon blocks the Sun's brilliant disk and reveals the stars beyond. The opportunity came on May 29, 1919, when a total solar eclipse would be visible from the South Atlantic. British astronomer Arthur Eddington organised two expeditions, one to the island of Principe off the coast of West Africa and another to Sobral in northern Brazil. Despite cloudy weather that threatened to ruin the observations, both teams successfully photographed stars near the Sun during totality. When the photographic plates were developed and carefully measured, they revealed star positions shifted by amounts consistent with Einstein's predictions. Light from distant stars had indeed been bent by the Sun's gravitational field, following curved paths through the warped space-time surrounding our nearest star. The universe operated according to Einstein's geometric vision, not Newton's mechanical one. News of this confirmation spread rapidly around the world. The London Times proclaimed "Revolution in Science and New Theory of the Universe." Einstein became an international celebrity overnight, his name synonymous with genius, and his theory synonymous with the overthrow of absolute space and time. But the implications of general relativity extended far beyond the bending of starlight. If space-time could be curved by matter and energy, then it could potentially be curved in ways that created closed loops, regions where time itself circled back on itself. It could be stretched and compressed, twisted and torn. The placid, unchanging stage of Newton's universe was revealed to be a dynamic, responsive medium capable of extraordinary behavior. Karl Schwarzschild, a German physicist and astronomer serving on the Russian front during World War I, became the first person to find an exact solution to Einstein's field equations. Working by candlelight in his military tent, Schwarzschild investigated what space-time would look like around a perfectly spherical mass. His solution described a geometry so extreme that it predicted regions where space-time curvature becomes infinite, places where the normal laws of physics break down completely. These solutions seemed so bizarre that even Einstein initially dismissed them as mathematical curiosities with no physical reality. The Schwarzschild geometry predicted that if enough mass were compressed into a small enough volume, it would create a region of space-time so severely curved that nothing, not even light itself, could escape. The boundary of this region, now called the event horizon, would mark a point of no return where the curvature of space-time overwhelms any attempt to travel back to the outside universe. We now know these objects as black holes, among the most exotic and powerful phenomena in the cosmos. They represent space-time curvature taken to its ultimate extreme, places where Einstein's geometric vision of gravity produces effects so dramatic that they strain the limits of human imagination. Near a black hole, time slows to a crawl, as measured by distant observers. Space itself seems to stretch and distort, and the distinction between cause and effect becomes blurred. Einstein's field equations also predicted that space-time itself could be dynamic on the largest scales. In 1922, Russian physicist Alexander Friedmann discovered solutions describing a universe that expands or contracts over time. The fabric of space-time itself could grow larger or smaller, carrying galaxies along like raisins in rising bread dough. This prediction seemed so outlandish that Einstein initially rejected it, preferring to believe in a static, unchanging cosmos. But observations by Edwin Hubble in the late 1920s revealed that distant galaxies are indeed receding from us, their light stretched to redder wavelengths by the expansion of space itself. The universe was not static but dynamic, growing larger with each passing moment in accordance with Einstein's geometric equations. Space itself was expanding, creating new volume between galaxies, while the galaxies themselves remained essentially unchanged. These discoveries revealed that space-time is not merely curved by matter and energy, it is alive with motion and change. The fabric of reality stretches and flows, creating the stage upon which cosmic evolution unfolds. Galaxies form and evolve, stars are born and die, and the universe itself grows older and larger, all within the dynamic framework of Einstein's curved space-time. The geometric interpretation of gravity also provided new insights into the nature of orbits and trajectories. In Newton's universe, planets orbit the Sun because they are constantly pulled inward by gravitational force, their inertial tendency to travel in straight lines balanced against the Sun's gravitational tug. But in Einstein's curved space-time, planets simply follow geodesics, the straightest possible paths through the curved geometry created by the Sun's presence. From this perspective, Earth is not being pulled toward the Sun at all. Instead, Earth travels through space-time along the path of least resistance, a path that happens to curve around the Sun because of the way the Sun's mass warps the geometry of space-time. What we perceive as an orbit is actually an object following a straight line through curved, four-dimensional space-time, much as an airplane follows a great circle route across the curved surface of Earth. This geometric view explains why orbits are stable over enormous periods of time. Planets don't gradually spiral into the Sun because they're not fighting against some external force. They're simply following the natural geometry of space-time, paths that remain constant as long as the underlying curvature remains unchanged. The solar system is not a collection of objects held together by mysterious forces. It is a family of worlds following the geometric contours of curved space-time. Einstein's revolution was now complete. Gravity, the mysterious force that had puzzled Newton and his successors for centuries, was revealed to be an illusion created by our limited perspective. What we experience as gravitational force is actually the curvature of space-time, made manifest in the motion of matter and energy. The universe operates not through forces acting across empty space, but through the dynamic geometry of space-time itself. This geometric vision would lead to even more remarkable predictions. Waves rippling through space-time itself, carrying information about cosmic catastrophes across billions of light years. But first, Einstein's theory would face its greatest tests, confronting phenomena so extreme that they would challenge the very limits of mathematical physics and human understanding. The most beautiful theory in the world is worthless if it cannot survive the harsh scrutiny of experimental verification. Einstein's geometric vision of gravity, elegant though it was, would mean nothing unless it could make predictions that could be tested, measured, and confirmed through observation. The transformation from mathematical hypothesis to accepted physical law would require a century of increasingly precise experiments, each one probing deeper into the fabric of space-time itself. The first major test had already passed with flying colours. Eddington's eclipse observations of 1919 confirmed that massive objects bend light exactly as Einstein's equations predicted. But skeptics remained unconvinced. Perhaps the effect was caused by refraction in the sun's atmosphere, or systematic errors in the photographic measurements, or wishful thinking on the part of experimenters eager to confirm a revolutionary theory. What Einstein's theory needed was not just one dramatic confirmation, but a sustained campaign of verification across multiple phenomena, different scales, and various experimental techniques. The predictions had to be so precise, so unambiguous, and so repeatedly confirmed that even the most determined skeptic would be forced to accept the reality of curved space-time. The second major triumph came from an unexpected source: the Global Positioning System, a constellation of satellites originally designed for military navigation, but now essential to countless civilian applications. GPS satellites orbit Earth at an altitude of 12,400 miles, traveling at speeds of 8,600 miles per hour. At this altitude and velocity, the effects of Einstein's relativity become crucial for accurate positioning. According to special relativity, the atomic clocks aboard GPS satellites should run slower than identical clocks on Earth's surface because of their high orbital velocity. The time dilation effect amounts to about 7 microseconds per day. But according to general relativity, those same clocks should run faster than surface clocks because they experience weaker gravitational fields at their orbital altitude. This gravitational time dilation effect amounts to about 45 microseconds per day. The net result is that satellite clocks gain approximately 38 microseconds per day compared to Earth-based clocks. This might seem like a trivial difference, but GPS accuracy depends on measuring the time it takes radio signals to travel from satellites to receivers. Light travels about 1 foot per nanosecond, so a timing error of 38 microseconds per day would translate to positioning errors of over 6 miles per day. Without Einstein's relativistic corrections, GPS would be useless for navigation. Every smartphone that displays your location, every navigation system that guides you to your destination, every autonomous vehicle that drives itself safely down the highway depends on engineers incorporating Einstein's predictions about curved spacetime into their calculations. General relativity is not abstract theory, it is practical technology that affects millions of lives every day. But GPS represents just one example of how space-time curvature affects everyday technology. Atomic clocks, the most precise timekeeping devices ever created, must account for gravitational time dilation whenever they are moved to different altitudes. The cesium fountain clocks that define the international time standard run differently at different elevations, requiring constant corrections to maintain synchronization across the global timekeeping network. Even more dramatic confirmation came from observations of binary pulsars, exotic stellar remnants that function as natural laboratories for testing general relativity under extreme conditions. Pulsars are neutron stars, the collapsed cores of massive stars that have undergone supernova explosions. These objects pack more mass than the Sun into a sphere only 12 miles across, creating gravitational fields so intense that they warp space-time in measurable ways. The first binary pulsar was discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope in Puerto Rico. This system, designated PSR B1913+16, consists of two neutron stars orbiting each other every 7 hours and 45 minutes. One of the neutron stars is a pulsar spinning 30 times per second and sweeping a beam of radio waves across space like a cosmic lighthouse. The pulsar's radio signals provide an incredibly precise clock, allowing astronomers to measure the orbital motion of the binary system with extraordinary accuracy. According to general relativity, two massive objects orbiting each other should gradually lose energy by radiating gravitational waves, ripples in space-time itself that carry energy away from the system. As the system loses energy, the two neutron stars should spiral slowly inward, causing their orbital period to decrease. Hulse and Taylor monitored the binary pulsar for years, timing the arrival of radio pulses with nanosecond precision. They found that the orbital period was indeed decreasing by exactly the amount predicted by Einstein's equations. The two neutron stars were spiraling toward each other at a rate of 3 millimeters per orbit, losing energy to gravitational radiation in perfect agreement with general relativity. This discovery provided the first indirect evidence for gravitational waves, confirming another exotic prediction of Einstein's geometric theory. Hulse and Taylor shared the 1993 Nobel Prize in Physics for their work, which demonstrated that space-time is not only curved by matter and energy, but can actually ripple and vibrate like the surface of a disturbed pond. Meanwhile, laboratory experiments were pushing the precision of gravitational tests to unprecedented levels. The equivalence principle, which states that gravitational and inertial acceleration are identical, became the subject of increasingly sensitive measurements. If general relativity is correct, all objects should fall with exactly the same acceleration in a gravitational field, regardless of their composition. The most precise tests use sophisticated devices called torsion balances, which can detect tiny differences in gravitational acceleration between different materials. Modern experiments have confirmed the equivalence principle to better than 1 part in 10 trillion, meaning that if you dropped a kilogram of aluminum and a kilogram of platinum from the same height, they would strike the ground within less than 1 picosecond of each other. These tests also search for violations of the equivalence principle that might reveal new physics beyond general relativity. Some theories of quantum gravity predict that different types of matter might respond slightly differently to gravitational fields, creating detectable deviations from Einstein's predictions. So far, no such deviations have been found, but the search continues with ever-increasing precision. Frame dragging represents another exotic prediction of general relativity that has been confirmed through careful observation. According to Einstein's theory, rotating masses should drag space-time around with them, like honey being stirred by a rotating spoon. This effect, also called the Lenz-Thirring effect after the Austrian physicists who first calculated it, is extremely small for ordinary objects, but becomes measurable near massive, rapidly rotating bodies. NASA's Gravity Probe B mission, launched in 2004, was specifically designed to measure frame dragging around Earth. The spacecraft carried 4 gyroscopes, the most perfect spheres ever manufactured, each one uniform to within 40 atoms across its surface. These gyroscopes were suspended in vacuum and cooled to near absolute zero to eliminate all disturbances except the subtle effects of curved spacetime. As Gravity Probe B orbited Earth, the orientations of its gyroscopes slowly changed due to 2 relativistic effects. The geodetic effect, caused by Earth's mass curving spacetime, changed the gyroscope orientations by about 6.6 arcseconds per year. The frame dragging effect, caused by Earth's rotation twisting spacetime, produced an additional change of only 39 milliarcseconds per year. about the width of a human hair seen from 10 miles away. After decades of data analysis to separate these tiny signals from instrumental noise and systematic errors, the Gravity Probe B team confirmed both effects within the measurement uncertainties. Earth's rotation does indeed drag spacetime around with it, exactly as Einstein's equations predict. The fabric of spacetime near our planet is not only curved by Earth's mass, but also twisted by its rotation. Gravitational lensing has become one of the most powerful tools for testing general relativity on cosmic scales. When light from distant galaxies passes near massive objects like galaxy clusters, the curved spacetime bends the light rays, creating distorted, magnified images of the background sources. This effect turns massive galaxy clusters into natural telescopes, allowing astronomers to study objects that would otherwise be too faint to observe. The lensing effects are so precisely predictable using Einstein's equations that astronomers can use them to map the distribution of dark matter in galaxy clusters. Dark matter, which makes up about 27% of the universe's total mass energy, but interacts only gravitationally with ordinary matter, reveals its presence through the way it bends light from background galaxies. Some of the most dramatic examples of gravitational lensing create multiple images of the same distant galaxy, arranged in rings or arcs around the lensing cluster. The time delays between these multiple images provide additional tests of general relativity, as light following different paths through curved spacetime takes different amounts of time to reach Earth. Supermassive black holes at the centers of galaxies provide natural laboratories for testing general relativity under the most extreme conditions accessible to observation. The Event Horizon Telescope, a global network of radio telescopes working together, has captured images of the event horizons of two supermassive black holes, one in the galaxy M87 and another in our own Milky Way galaxy. These images show glowing rings of hot gas orbiting the black holes at significant fractions of the speed of light. The size and shape of these rings, the way the light is distorted and redshifted by the black hole's gravitational field, and the motion of bright spots in the accretion disk all provide detailed tests of Einstein's predictions about spacetime curvature near black holes. Stars orbiting close to the supermassive black hole at the center of our galaxy offer another precision test of general relativity. Astronomers have tracked the motion of individual stars as they follow highly elliptical orbits around the central black hole, sometimes approaching within a few light hours of the event horizon. These observations reveal relativistic effects including orbital precession, gravitational redshift, and Doppler boosting, all in excellent agreement with Einstein's theory. Perhaps the most remarkable aspect of these tests is their consistency across an enormous range of scales and conditions. From GPS satellites orbiting 12,000 miles above Earth to binary pulsars in distant galaxies. From laboratory experiments measuring tiny differences in gravitational acceleration to cosmic observations of light bent by galaxy clusters. Every test confirms the same fundamental insight. Spacetime is a dynamic, curved fabric that responds to the presence of matter and energy. This consistency is not accidental. It reflects the deep unity underlying Einstein's geometric vision of gravity. Unlike Newton's theory, which treated gravity as a force that could potentially be modified by unknown mechanisms, general relativity emerges from fundamental principles about the nature of spacetime itself. The theory's predictions are not arbitrary, but follow inevitably from the assumption that gravity is spacetime curvature. Yet even as observation after observation confirms Einstein's theory, new tests continue to push the boundaries of precision and explore previously inaccessible regimes. Atomic interferometers can now measure gravitational acceleration with unprecedented sensitivity. Space-based gravitational wave detectors will probe the merger of massive black holes billions of light years away. Next-generation atomic clocks will test the equivalence principle with even greater precision. Each new test serves not only to verify general relativity, but also to search for deviations that might reveal new physics beyond Einstein's theory. Most physicists expect that general relativity, like all physical theories, will eventually be superseded by a more comprehensive theory that unifies gravity with quantum mechanics. But after more than a century of increasingly precise tests, Einstein's geometric vision of space-time remains unchallenged. The success of these tests has transformed general relativity from a speculative theory into the foundation of modern physics and technology. GPS navigation, atomic timekeeping, astronomical observation, and fundamental physics research all depend on Einstein's insights about curved spacetime. What began as an abstract mathematical theory has become an essential tool for understanding and navigating the cosmos. But perhaps the most profound implication of these experimental confirmations is what they reveal about the nature of reality itself. We live not in Newton's clockwork universe of forces acting across rigid space and absolute time, but in Einstein's dynamic cosmos, where space and time form a unified fabric that bends, stretches, and curves in response to matter and energy. Every GPS measurement, every atomic clock correction, every astronomical observation reminds us that we are embedded in this curved space-time, participants in the cosmic dance between matter and geometry that shapes the universe at every scale. In the depths of space, 26,000 light-years from Earth, something invisible and monstrous lurks at the heart of our galaxy. It weighs as much as 4 million suns, yet occupies a region smaller than our solar system. It devours nearby stars, tears apart gas clouds with tidal forces that stretch matter into glowing streams, and warps space-time so severely that the normal laws of physics break down at its center. This is Sagittarius A star, a supermassive black hole that demonstrates Einstein's most extreme prediction. Regions where space-time curvature becomes so intense that it tears holes in the fabric of reality itself. The story of black holes begins not with astronomical observation, but with mathematical inevitability. Within months of Einstein publishing his field equations in 1915, physicists began searching for exact solutions that could describe space-time around massive objects. The first breakthrough came from Karl Schwarzschild, a German astronomer and mathematician serving on the Russian front during World War I. Working by lamplight in freezing military trenches, Schwarzschild solved Einstein's equations for the space-time geometry around a perfectly spherical mass. His solution revealed something that even Einstein found difficult to accept. If enough mass were concentrated within a sufficiently small radius, it would create a region of space-time so severely warped that nothing could escape from it, not even light itself. The critical radius, now called the Schwarzschild radius, depends only on the mass of the central object. For an object with the mass of our Sun, this radius would be about 3 kilometers. For Earth, it would be less than 1 centimeter. As long as the actual radius of the object remains larger than its Schwarzschild radius, space-time remains well behaved. But if all that mass could somehow be compressed within the Schwarzschild radius, something extraordinary would happen. At the Schwarzschild radius, space-time curvature becomes so extreme that the normal relationship between space and time breaks down completely. This boundary, which we now call the event horizon, marks a point of no return. Anything that crosses this invisible surface becomes causally disconnected from the rest of the universe, doomed to fall inexorably toward the center, where space-time curvature becomes infinite. The name black hole wouldn't be coined until 1967, when physicist John Wheeler used the term during a lecture at Columbia University. Before that, these objects were called frozen stars, or dark stars, or simply gravitationally collapsed objects. But Wheeler's vivid phrase captured the essential nature of these cosmic monsters. They are holes torn in space-time itself, regions where the normal structure of reality simply ceases to exist. For decades after Schwarzschild's discovery, most physicists regarded black holes as mathematical curiosities with no counterpart in the real universe. How could any physical process actually create such extreme conditions? The pressures required to compress ordinary matter to nuclear densities seemed impossible to achieve. Even if such compression occurred, surely some unknown force would halt the collapse before the Schwarzschild radius was reached. The answer came from studies of stellar evolution. Stars shine by converting hydrogen into helium in their cores, releasing enormous amounts of energy that create outward pressure to balance the inward pull of gravity. But this nuclear fuel is finite. When a massive star exhausts its nuclear fuel, gravity finally wins the billion-year battle against radiation pressure. For stars with masses less than about 3 times the mass of the Sun, the collapse halts when matter is compressed to the density of atomic nuclei, creating neutron stars. But for more massive stars, not even the nuclear forces that hold neutrons together can resist the crushing weight of gravity. The collapse continues without any known force capable of stopping it. According to general relativity, this runaway gravitational collapse inevitably leads to the formation of a black hole. As the star's surface shrinks past the Schwarzschild radius, it disappears from view, leaving behind only its gravitational influence on the surrounding space-time. The matter itself continues falling toward the center, where it encounters a singularity, a point where density becomes infinite, and the curvature of space-time becomes mathematically undefined. But black holes are not cosmic vacuum cleaners that suck in everything around them. Far from a black hole, space-time is curved, but not dramatically different from the space-time around any other massive object. Earth could orbit a black hole with the same mass as the Sun, just as easily as it orbits the actual Sun. The difference only becomes apparent when objects venture close to the event horizon. Near the event horizon, the effects of extreme space-time curvature become impossible to ignore. Time dilation becomes so severe that processes near the horizon appear frozen when viewed by distant observers. An astronaut falling toward a black hole would appear to slow down and fade away as her light becomes increasingly redshifted, but she would never actually be seen to cross the event horizon. From her perspective, however, the journey to the center would take only a finite amount of proper time. The tidal forces near a black hole present another deadly hazard. Because gravity weakens with distance, an object falling feet first toward a black hole experiences stronger gravitational pull on its feet than on its head. For stellar mass black holes, these tidal forces become lethal long before the event horizon is reached, stretching the unfortunate traveler into a thin strand of matter in a process grimly dubbed spaghettification. For decades, black holes remained theoretical entities, predicted by mathematics but unobserved by astronomy. They emit no light of their own and absorb any light that falls on them, making direct detection seemingly impossible. How do you observe something that is, by definition, invisible? The breakthrough came from understanding how black holes interact with their surroundings. While isolated black holes remain invisible, black holes that are part of binary star systems can reveal themselves through their gravitational effects on their companions. If a black hole orbits close to a normal star, it can strip matter from the star's outer layers, creating a hot, glowing accretion disk that spirals inward toward the event horizon. The first convincing black hole candidate was discovered in 1971 in the constellation Cygnus. Cygnus X1, as it became known, is an intense source of X-rays located about 6,000 light-years from Earth. Observations revealed that the X-rays come from hot gas orbiting an invisible massive object with a mass at least 10 times greater than the Sun. The normal star in this system is a blue supergiant, massive and luminous, but losing matter to its invisible companion. As this matter falls toward the black hole, it heats up to millions of degrees, and emits the X-rays that first drew astronomers' attention. The orbital characteristics of the system, combined with the mass estimate for the invisible object, strongly suggested that Cygnus X1 contains a black hole. But confirmation required more than circumstantial evidence. Astronomers needed to measure the mass of the invisible object with sufficient precision to rule out alternative explanations like neutron stars or white dwarf stars. This required detailed studies of the orbital motion, careful analysis of the X-ray emissions, and sophisticated modeling of the accretion process. The evidence gradually became overwhelming. Dozens of similar systems were discovered throughout our galaxy, each one containing a normal star orbiting an invisible massive companion. In case after case, the mass of the invisible object exceeded the theoretical maximum for neutron stars, leaving black holes as the only viable explanation. Meanwhile, astronomers were discovering evidence for much more massive black holes at the centers of galaxies. These supermassive black holes, containing millions or billions of times the mass of the Sun, power some of the most energetic phenomena in the universe. Active galactic nuclei, quasars, and radio galaxies all derive their enormous energy output from matter falling into supermassive black holes. The supermassive black hole at the center of our own galaxy provided a unique opportunity to study black hole physics in unprecedented detail. Unlike the distant black holes powering quasars billions of light years away, Sagittarius A star is close enough that astronomers can track the motion of individual stars in its vicinity. Using adaptive optics to correct for atmospheric turbulence, astronomers began monitoring stars orbiting near the galactic center. One star, designated S2, follows a highly elliptical orbit that brings it within about 75 astronomical units of the black hole every 16 years. At its closest approach, S2 travels at speeds exceeding 15 million miles per hour, allowing astronomers to test Einstein's predictions about motion in strong gravitational fields. These observations revealed clear evidence of relativistic effects. The star's orbit precesses, rotating slowly over time due to the curvature of spacetime near the black hole. The star's light is gravitationally redshifted as it climbs out of the black hole's gravitational well. These effects match Einstein's predictions with remarkable precision, providing some of the strongest evidence that supermassive black holes exist and behave exactly as general relativity predicts. But the most dramatic confirmation of black hole physics came from an entirely new type of observation: direct imaging of black hole event horizons. The Event Horizon Telescope, a global network of radio telescopes working together to create an Earth-sized interferometer, achieved the seemingly impossible goal of photographing a black hole. The first target was the supermassive black hole in the galaxy M87, located 54 million light-years away in the constellation Virgo. This black hole, with a mass 6.5 billion times that of the Sun, is surrounded by a glowing accretion disk of hot gas. The Event Horizon Telescope captured the shadow of the black hole against this glowing background, revealing the dark silhouette of the event horizon itself. The image shows a bright ring of emission surrounding a dark central region about 2.5 times the size of the black hole's event horizon. This shadow results from the extreme bending of light rays near the black hole, which creates a region where no photons can reach distant observers. The size and shape of this shadow match theoretical predictions with stunning accuracy, providing direct visual evidence that black holes exist and possess event horizons exactly as Einstein's theory predicts. The Event Horizon Telescope later captured an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Despite being much closer than M87's black hole, Sagittarius, a star, presented greater observational challenges because the hot gas around it changes on timescales of minutes rather than days. The resulting image required sophisticated analysis to reconstruct a stable picture from rapidly varying data. These images represent more than just remarkable technical achievements. They provide direct confirmation that black holes are real astronomical objects, not merely mathematical abstractions. The dark shadows visible in these images are the first direct observations of event horizons, the boundaries where space-time curvature becomes so extreme that not even light can escape. Black holes also serve as natural laboratories for testing our understanding of fundamental physics. The extreme conditions near event horizons allow physicists to study the behavior of matter and energy in gravitational fields far stronger than anything achievable in terrestrial laboratories. Observations of matter spiraling into black holes reveal how gases behave at temperatures of millions of degrees and densities approaching those found in atomic nuclei. The merger of two black holes creates some of the most violent events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. These collisions, detected by gravitational wave observatories like LIGO and Virgo, provide unique insights into the behavior of space-time itself under the most extreme conditions imaginable. As matter falls past the event horizon of a black hole, it appears to freeze at the boundary when viewed by distant observers, its light becoming infinitely redshifted and dimmed. But this is an illusion created by the extreme time dilation near the event horizon. From the perspective of the falling matter itself, the journey continues inexorably toward the center, where it encounters conditions so extreme that our current understanding of physics breaks down completely. At the center of every black hole lies a singularity, a point where the curvature of space-time becomes infinite and the normal laws of physics cease to apply. Here, general relativity itself reaches its limits, predicting conditions so extreme that quantum effects must become important. Understanding what happens at these singularities will likely require a complete theory of quantum gravity, unifying Einstein's geometric vision of space-time with the probabilistic principles of quantum mechanics. Black holes thus represent both the ultimate triumph and the ultimate limitation of Einstein's general relativity. They demonstrate that space-time can indeed be torn and twisted into configurations so extreme that they create holes in the fabric of reality itself. Yet they also point toward new physics beyond general relativity, phenomena that will require revolutionary new insights to understand fully. In pushing space-time to its breaking point, black holes illuminate both what we know and what we have yet to discover about the deepest structure of the universe. September 14th, 2015, at 9:51 Greenwich Mean Time. For the first time in human history, ripples in the fabric of space-time itself washed over Earth, stretching and compressing the distance between atoms by less than 1/10,000th the width of a proton. These ghostly disturbances had traveled for 1.3 billion years across the cosmos, carrying news of a cosmic catastrophe so violent that it released more energy in gravitational waves than all the visible stars in the observable universe emit as light. Two black holes, each roughly 30 times the mass of the Sun, had spiraled into each other in a dance of destruction that lasted mere seconds, but shook the very foundations of space and time. As they merged, they converted 3 solar masses worth of matter directly into pure gravitational radiation, sending ripples spreading outward through space-time at the speed of light. When these ripples finally reached Earth, they were detected by the most sensitive measuring instruments ever constructed, the twin laser interferometer, gravitational wave observatory detectors in Louisiana and Washington state. This detection marked the dawn of gravitational wave astronomy, opening an entirely new window on the universe and confirming one of Einstein's most audacious predictions. A century earlier, Einstein had realized that if space-time could be curved and distorted by matter and energy, then sudden changes in those distortions should propagate outward as waves, like ripples spreading across the surface of a pond after a stone is thrown into the water. The mathematical prediction emerged naturally from Einstein's field equations. When matter accelerates, particularly when massive objects undergo rapid changes in their motion, they should create oscillations in the curvature of space-time itself. These gravitational waves would travel at the speed of light, carrying energy away from their source and gradually weakening as they spread across ever larger volumes of space. But Einstein himself was ambivalent about whether gravitational waves actually existed. The mathematics was subtle, and the effects seemed impossibly weak. In 1916, he published a paper claiming that gravitational waves were real. 2 years later, he published another paper arguing that they were merely mathematical artifacts with no physical reality. Even into the 1930s, Einstein continued to waver on the question, sometimes convinced of their existence, sometimes convinced they were illusions created by coordinate choices in the mathematical formalism. The confusion arose partly from the peculiar nature of gravitational waves themselves. Unlike electromagnetic waves, which can be detected by measuring the forces they exert on charged particles, gravitational waves cannot be shielded or absorbed by ordinary matter. They pass through solid rock, molten iron, and human flesh with equal ease, barely interacting with anything in their path. Detecting them requires measuring their effect on the fabric of space-time itself. The theoretical foundation for gravitational waves was finally established in the 1950s and 60s through the work of physicists like Hermann Bondi, Felix Pirani, and Ivor Robinson. They showed that gravitational waves are indeed real, physical phenomena that carry energy and momentum away from their sources. When a gravitational wave passes through a region of space-time, it alternately stretches and compresses distances in perpendicular directions, creating a characteristic quadrupole pattern of distortion. Imagine a ring of freely floating particles arranged in a circle. As a gravitational wave passes through the ring, traveling perpendicular to the plane of the circle, the particles would oscillate back and forth. When the wave stretches space in one direction, it simultaneously compresses space in the perpendicular direction. Half a wavelength later, the pattern reverses. Regions that were stretched become compressed, and regions that were compressed become stretched. This oscillatory stretching and compressing of space itself provides the key to detecting gravitational waves. If you could measure distances with sufficient precision, you could detect the tiny changes in length that occur as gravitational waves pass by. But the challenge is daunting. Even the most powerful gravitational wave sources in the universe produce effects that change distances by less than 1 part in 10 to the 21st power. To put this in perspective, imagine trying to measure the distance from Earth to the nearest star, Proxima Centauri, to an accuracy smaller than the width of a human hair. That's roughly the precision required to detect gravitational waves from cosmic sources. Such measurements seemed impossible with any conceivable technology when Einstein first predicted gravitational waves in 1916. The breakthrough came from an unexpected source, the invention of the laser in 1960. Coherent light beams could be used to measure distances with extraordinary precision through a technique called interferometry. By splitting a laser beam and sending the two halves down perpendicular arms of equal length, then recombining them, tiny changes in the length of either arm could be detected as shifts in the interference pattern where the beams meet. Rainer Weiss at MIT developed the first detailed design for a laser interferometer gravitational wave detector in 1972. His proposal called for kilometer-scale instruments with laser beams traveling back and forth along perpendicular arms. As gravitational waves passed through the detector, they would alternately lengthen one arm while shortening the other, creating detectable phase shifts in the recombined laser light. But building such detectors proved to be one of the most challenging technological undertakings in the history of experimental physics. The required sensitivity pushed the boundaries of vacuum technology, vibration isolation, laser stabilization, and optical engineering. Every conceivable source of noise had to be eliminated or controlled. Seismic vibrations from distant earthquakes, acoustic disturbances from passing aircraft, thermal fluctuations in the detector components, even the quantum shot noise inherent in laser light itself. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, began construction in the 1990s at 2 sites separated by 3,000 kilometers. Each facility houses an L-shaped detector with arms 4 kilometers long, making them among the largest precision instruments ever built. Ultra-high vacuum systems maintain pressures lower than those found in interplanetary space. Multiple stages of vibration isolation protect the optical components from ground motion. Powerful lasers are stabilized to frequency precisions of 1 part in 10 to the 21st power. For years, LIGO searched for gravitational waves without success. The detectors were sensitive enough to measure length changes smaller than 1/10,000th the width of a proton. But even this extraordinary sensitivity was not quite enough to detect the weak gravitational waves reaching Earth from cosmic sources. The silence was frustrating, but not entirely surprising. Theoretical calculations suggested that detection would require even greater sensitivity. The solution came through a major upgrade completed in 2015. Advanced LIGO incorporated more powerful lasers, better vibration isolation, improved mirror coatings, and sophisticated quantum noise reduction techniques. The enhanced sensitivity increased the volume of space from which gravitational waves could be detected by more than a factor of 1,000, dramatically improving the chances of making a detection. The first gravitational wave signal, designated GW150914, arrived just days after advanced LIGO began taking data. The characteristic signature was unmistakable, a rapid increase in frequency and amplitude lasting about 0.2 of a second that matched theoretical templates for the merger of 2 black holes with remarkable precision. Computer simulations of black hole mergers had predicted exactly this type of signal. As 2 black holes spiral toward each other, they emit gravitational waves that carry away energy and angular momentum, causing the orbit to decay. The gravitational wave frequency increases as the black holes move faster and closer together, producing a distinctive chirp that rises in both frequency and amplitude until the black holes merge. The LIGO detection allowed astronomers to reconstruct the entire merger process in unprecedented detail. The 2 black holes had masses of 36 and 29 solar masses, making them among the most massive stellar black holes ever discovered. They had been orbiting each other for millions of years, gradually spiraling inward as they lost energy to gravitational radiation. In the final seconds before merger, the black holes were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. The gravitational wave signal captured the last 20 orbits before the black holes touched, merged into a single black hole of 62 solar masses, and settled into a quiescent state. 3 solar masses of matter had been converted directly into gravitational wave energy, briefly outshining all the stars in the observable universe. This detection opened the floodgates for gravitational wave astronomy. Within months, LIGO detected additional black hole mergers, each one revealing new insights into the population of massive black holes in the universe. The discovered black holes were more massive than most stellar black holes observed through electromagnetic radiation, suggesting that gravitational waves were revealing a previously hidden population of cosmic objects. The most spectacular discovery came on August 17, 2017, when LIGO detected the merger of 2 neutron stars. Unlike black hole mergers, which produce only gravitational waves, neutron star mergers create electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This multi-messenger event, designated GW170817, was detected by gravitational wave observatories and followed up by telescopes around the world. The electromagnetic observations revealed that neutron star mergers are cosmic foundries for heavy elements. The collision ejected about 1% of a solar mass worth of neutron-rich matter into space, where rapid neutron capture processes forge gold, platinum, uranium, and other elements heavier than iron. The total amount of gold created in this single event was greater than the mass of Earth, instantly doubling the known rate of heavy element production in the universe. These observations solved a long-standing mystery about the origin of heavy elements. While lighter elements up to iron are created in the cores of massive stars, the production sites for heavier elements had remained uncertain. The neutron star merger provided direct evidence that these cosmic collisions are responsible for creating much of the gold, platinum, and other precious metals found on Earth and throughout the universe. Gravitational wave detections have also provided new tests of Einstein's general relativity under extreme conditions. The propagation speed of gravitational waves, measured by comparing their arrival times at multiple detectors, matches the speed of light to within 1 part in 10 to the 15th power. The polarization patterns of the waves match Einstein's predictions exactly. The rate at which merging black holes lose energy to gravitational radiation agrees with theoretical calculations to extraordinary precision. Perhaps most remarkably, gravitational waves have allowed scientists to test the behavior of spacetime itself under the most extreme conditions in the universe. Near merging black holes, spacetime curvature becomes so intense that the fabric of reality oscillates violently, stretching and compressing by significant fractions while maintaining the precise mathematical relationships predicted by Einstein's equations. The Virgo detector in Italy joined the gravitational wave network in 2017, followed by Kagra in Japan in 2020. Multiple detectors allow astronomers to triangulate the positions of gravitational wave sources, enabling rapid follow-up observations with conventional telescopes. This network approach has transformed gravitational wave astronomy from a discovery science into a precision measurement tool. Future gravitational wave detectors will push sensitivity to even greater extremes. The proposed Cosmic Explorer, with arms 40 kilometers long, could detect neutron star mergers throughout the observable universe. Space-based detectors like the Laser Interferometer Space Antenna, or LISA, will open entirely new frequency ranges, detecting gravitational waves from sources as diverse as white dwarf binaries in our galaxy and supermassive black hole mergers at cosmic dawn. These future observations will probe gravitational phenomena currently beyond our reach. LISA will detect the gravitational waves from millions of white dwarf binaries in our galaxy, creating a cosmic gravitational wave background that reveals the structure and evolution of stellar populations. It will observe the formation and growth of supermassive black holes in the early universe, providing insights into how the first galaxies assembled. Gravitational waves have also opened new avenues for testing fundamental physics. The propagation of gravitational waves through cosmological distances provides tests of general relativity on the largest scales in the universe. Deviations from Einstein's predictions could reveal modifications to gravity that become important at cosmic scales, potentially explaining the accelerating expansion of the universe without invoking dark energy. The precision of gravitational wave measurements continues to improve with each new detection. Advanced LIGO+, an ongoing upgrade, will increase sensitivity by another factor of 2. Third-generation detectors like Einstein Telescope and Cosmic Explorer will improve sensitivity by orders of magnitude, detecting thousands of gravitational wave sources per year and enabling detailed studies of cosmic evolution through gravitational wave archaeology. Perhaps most profoundly, gravitational waves have confirmed that spacetime itself is a dynamic, responsive medium that can vibrate and carry information across cosmic distances. Einstein's field equations predicted not just that matter curves spacetime, but that changes in this curvature propagate as waves traveling at the speed of light. These waves carry pure information about the motion of matter and energy, unfiltered by the complex interactions that affect electromagnetic radiation. Gravitational waves thus represent the ultimate confirmation of Einstein's geometric vision of gravity. They demonstrate that space-time is not merely curved by matter and energy, but can oscillate, ripple, and carry energy in its own right. The fabric of reality itself has been revealed as a dynamic medium, capable of transmitting information about the most violent events in the universe across billions of years and billions of light years of space. When those first gravitational waves swept through Earth on September 14, 2015, they carried more than just news of a distant black hole merger. They brought confirmation that we live in Einstein's dynamic universe, where space-time itself participates actively in the cosmic dance of matter and energy, stretching and flexing and vibrating in response to the most energetic events the cosmos can produce. Deep beneath the Swiss Alps, in tunnels carved through solid rock, scientists have built the most powerful microscope ever conceived. The Large Hadron Collider accelerates protons to 99.9999991% of the speed of light, smashing them together with energies that recreate conditions not seen since the first trillionth of a second after the Big Bang. These collisions probe the fundamental structure of matter and energy at the smallest scales imaginable, revealing a quantum world that operates according to principles utterly alien to our everyday experience. Yet for all its power, the Large Hadron Collider cannot probe the most fundamental question in modern physics. What happens when Einstein's smooth, geometric description of space-time meets the probabilistic, uncertain realm of quantum mechanics? This collision between two of humanity's greatest intellectual achievements, general relativity and quantum theory, has created the deepest crisis in theoretical physics since the days of Galileo and Newton. The conflict emerges from the radically different ways these theories describe reality at its most basic level. General relativity presents a picture of space-time as a smooth, continuous fabric that curves and flows in response to matter and energy. This fabric extends infinitely in all directions, divisible into ever smaller regions without limit. Space and time form a seamless continuum where position and momentum can, in principle, be measured with arbitrary precision. Quantum mechanics tells a fundamentally different story. At the smallest scales, reality becomes grainy, uncertain, and inherently probabilistic. Particles exist in superpositions of multiple states simultaneously until measured. Position and momentum cannot both be known precisely due to Heisenberg's uncertainty principle. Energy and time are linked by quantum fluctuations that make the vacuum itself a seething foam of virtual particles constantly appearing and disappearing. These two descriptions of reality work magnificently within their respective domains. General relativity explains the motion of planets, the behavior of black holes, and the expansion of the universe with extraordinary precision. Quantum mechanics accounts for the stability of atoms, the operation of lasers, and the existence of computer chips with equal success. Yet when physicists try to combine them into a single unified theory, contradictions and infinities arise that have resisted resolution for nearly a century. The problem becomes acute when considering phenomena that involve both strong gravitational fields and quantum effects. Near the singularities at the centers of black holes, space-time curvature becomes so extreme that quantum effects should dominate the physics. Yet general relativity predicts infinite curvature where its own mathematical framework breaks down. In the first moments after the Big Bang, the entire observable universe was compressed into a region smaller than a proton, where both gravitational and quantum effects were equally important. Perhaps most troubling, the two theories make contradictory predictions about the nature of information and causality. General relativity is deterministic, given complete knowledge of space-time geometry and matter distribution. At one moment, Einstein's equations can predict the future evolution of the universe with certainty. Quantum mechanics is fundamentally probabilistic. Even with complete knowledge of a quantum system, only statistical predictions about future measurements can be made. The first hints that space-time itself might be quantized came from attempts to apply quantum mechanics to gravitational fields. Just as electromagnetic fields are quantized into photons, gravitational fields should be quantized into particles called gravitons. These hypothetical particles would be massless, travel at the speed of light, and carry the gravitational force between massive objects. But gravitons, if they exist, would interact so weakly with matter that they have never been directly detected. The quantum effects of gravity are suppressed by the Planck scale, a realm of distance and time so small that it exists far beyond the reach of any conceivable experiment. The Planck length, approximately 10 to the minus 35 meters, is 17 orders of magnitude smaller than a proton. At this scale, quantum fluctuations in space-time geometry itself should become important. At the Planck scale, the smooth fabric of space-time described by general relativity would break down into a quantum foam of constantly fluctuating geometry. Space and time themselves would become uncertain, subject to the same probabilistic principles that govern the behavior of subatomic particles. The very notion of a well-defined space-time background upon which both classical and quantum field theories depend would cease to have meaning. John Wheeler, who coined the term black hole, was among the first to envision this quantum foam. He imagined space-time at the Planck scale as a churning sea of virtual black holes and wormholes, constantly appearing and disappearing in accordance with quantum uncertainty principles. This foam would be invisible at larger scales, just as the molecular motion in a gas becomes invisible when viewed macroscopically, but it would represent the fundamental granular structure underlying apparently smooth space-time. The challenge of quantum gravity has inspired several ambitious theoretical approaches, each attempting to reconcile the geometric vision of general relativity with the probabilistic principles of quantum mechanics. String theory, perhaps the most famous of these approaches, proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in 11 dimensions of space-time. In string theory, particles are different vibrational modes of these fundamental strings, much as different musical notes correspond to different vibrational modes of a violin's string. Gravitons emerge naturally as one of these vibrational modes, automatically incorporating gravity into the quantum framework. The theory requires additional spatial dimensions beyond the three we observe, dimensions that are curled up or compactified at scales so small that they remain hidden from direct observation. String theory has achieved remarkable mathematical successes, providing a consistent framework for combining quantum mechanics and gravity without the infinities that plague other approaches. The theory makes contact with known physics at low energies, while predicting new phenomena at the Planck scale. Yet, despite decades of intensive research, string theory has not yet made testable predictions that could distinguish it from alternative approaches to quantum gravity. Loop quantum gravity takes a radically different approach, attempting to quantize space-time itself without invoking extra dimensions or exotic new particles. This theory suggests that space has a discrete, granular structure at the Planck scale, composed of quantum loops that weave together to form the fabric of space-time. Area and volume become quantized, taking on only specific, discrete values rather than varying continuously. In loop quantum gravity, the smooth space-time of general relativity emerges as an approximation valid at large scales, much as the smooth flow of water emerges from the discrete motion of individual molecules. The theory predicts that black hole singularities are replaced by quantum bounces that could give birth to new universes, and that the Big Bang itself might have been preceded by a contracting phase of space-time that underwent a quantum rebound. Emergent gravity represents another radical approach to the quantum gravity problem. Rather than treating space-time as fundamental, these theories propose that space-time emerges from more basic quantum information processing. In this view, the geometric properties of space-time, including its dimensionality and metric structure, arise from quantum entanglement between microscopic degrees of freedom. The holographic principle, inspired by studies of black hole thermodynamics, suggests that all the information in a volume of space-time can be encoded on its boundary. This principle implies that our three-dimensional reality might be a holographic projection of information stored on a two-dimensional surface, similar to how a hologram encodes three-dimensional images on flat photographic plates. These ideas have led to the ADS-CFT correspondence, a remarkable relationship discovered by Juan Maldacena in 1997. This correspondence establishes a precise mathematical equivalence between gravity in certain curved spacetimes and quantum field theories without gravity defined on the boundaries of those spacetimes. The correspondence provides a powerful tool for studying quantum gravity by translating difficult gravitational problems into more tractable quantum field theory calculations. Causal set theory proposes that spacetime is fundamentally discrete, composed of a finite number of point-like events connected by causal relationships. In this picture, the smooth spacetime of general relativity emerges as a statistical approximation to an underlying discrete structure, much as thermodynamics emerges from statistical mechanics. The theory attempts to derive both general relativity and quantum mechanics from purely combinatorial principles about causal relationships. Asymptotic safety offers yet another approach, suggesting that quantum gravity might be well defined at arbitrarily high energies if the theory possesses a special type of fixed point in its behavior. This approach attempts to extend general relativity into the quantum realm by finding a trajectory in the space of possible theories that remains finite and predictive at all energy scales. Despite their differences, all approaches to quantum gravity face similar conceptual challenges. The measurement problem of quantum mechanics becomes even more acute when applied to space-time itself. If space-time geometry is subject to quantum superposition, what determines when and how this superposition collapses into a definite classical geometry? How can we even define measurement when the measuring apparatus and the space-time in which it exists are both quantum mechanical? The information paradox presents another fundamental challenge. When matter falls into a black hole, quantum mechanics insists that the information it carries cannot be destroyed. Yet general relativity suggests that this information disappears forever behind the event horizon. Resolving this paradox may require radical revisions to our understanding of either quantum mechanics or general relativity, or both. Some physicists have proposed that the conflict between quantum mechanics and general relativity points toward entirely new principles of physics. The idea of emergent spacetime suggests that space and time are not fundamental features of reality, but collective phenomena that emerge from more basic quantum information processing, similar to how temperature emerges from molecular motion without being a fundamental property of individual molecules. Quantum error correction, originally developed for practical quantum computing, has provided new insights into the structure of space-time. The discovery that certain quantum error-correcting codes have geometric interpretations suggests that space-time geometry might encode quantum information in a fault-tolerant way, protecting it against local perturbations while maintaining global coherence. The study of quantum entanglement has revealed unexpected connections to space-time geometry. The Ryu-Takaya-Nagi correspondence relates the amount of entanglement between regions of a quantum system to the minimal surface area in a higher dimensional space-time. This relationship suggests that quantum entanglement might play a fundamental role in defining the geometric structure of space-time itself. Black hole thermodynamics has provided some of the most important clues about quantum gravity. The discovery that black holes have temperature and entropy proportional to their surface area rather than their volume suggests that the information in a gravitational system is encoded on its boundary rather than throughout its interior. This led to the formulation of the holographic principle and subsequent developments in quantum gravity research. The recent detection of gravitational waves has opened new avenues for testing quantum gravity theories. While current gravitational wave detectors are not sensitive enough to probe Planck-scale physics directly, future space-based detectors might be able to detect primordial gravitational waves from the quantum fluctuations that seeded cosmic structure formation. These observations could provide the first empirical constraints on quantum gravity theories. Precision tests of general relativity using atomic clocks, gravitational wave detectors, and astronomical observations continue to probe for deviations that might signal new physics beyond Einstein's theory. Any detected deviation would provide crucial guidance for developing quantum gravity theories, much as the photoelectric effect guided the development of quantum mechanics and the precession of Mercury's orbit guided the development of general relativity. The quest for quantum gravity represents more than an academic exercise in theoretical physics. Understanding how space-time behaves at the Planck scale could revolutionize our understanding of cosmology, revealing what happened in the first moments after the Big Bang and possibly resolving the singularity that general relativity predicts at the universe's beginning. It might explain the origin of the universe itself, showing how space-time and matter could emerge from purely quantum processes. Quantum gravity might also provide insights into the nature of dark matter and dark energy, mysterious components that comprise 95% of the universe yet remain poorly understood. Some quantum gravity theories predict new particles or modifications to gravitational physics that could account for these phenomena without invoking exotic new forms of matter and energy. Perhaps most profoundly, a successful theory of quantum gravity would complete the unification of physics begun by Maxwell's synthesis of electricity and magnetism. It would show how all fundamental forces and all forms of matter emerge from a single, underlying quantum description of reality. Such a theory would represent the culmination of humanity's quest to understand the deepest laws governing the cosmos. Yet this unification remains tantalizingly out of reach. The mathematics required to describe quantum gravity pushes the boundaries of human mathematical knowledge. The energy scales where quantum gravitational effects become important lie far beyond the reach of any conceivable experiment. The conceptual challenges require us to abandon intuitions about space, time, and causality that have guided physics for centuries. The resolution of the quantum gravity problem will likely require insights as revolutionary as those that led to quantum mechanics and general relativity themselves. It may demand new mathematical frameworks, new experimental techniques, or entirely new ways of thinking about the relationship between mathematics and physical reality. When that breakthrough comes, it will transform our understanding of the universe as profoundly as Einstein's geometric vision transformed our understanding of gravity itself. In the constellation Ursa Major, 13.8 billion light-years from Earth, a massive star exploded with such ferocity that for weeks it outshone its entire host galaxy. This supernova, designated SN 1997 FF, detonated when the universe was barely half its current age, yet its light carries a message that has revolutionized our understanding of cosmic destiny. The explosion was fainter than expected. Its light stretched to redder wavelengths by an amount that defied every prediction of standard cosmology. This single observation, along with dozens of similar distant supernovae studied in the 1990s, revealed one of the most shocking discoveries in the history of astronomy. The expansion of the universe is not slowing down as gravity pulls matter together, but accelerating as space itself grows larger at an ever-increasing rate. Something is pushing the cosmos apart, with a force so powerful that it overwhelms the gravitational attraction of all the matter and energy we can observe. The story begins with Alexander Friedmann's solutions to Einstein's field equations in 1922. Friedmann, a Russian physicist and mathematician, discovered that general relativity does not permit a static universe. Spacetime itself must either expand or contract on the largest scales, carrying galaxies along like raisins in rising or collapsing bread dough. This was so contrary to the prevailing view of an eternal, unchanging cosmos that even Einstein initially rejected Friedmann's mathematics. Einstein's resistance stemmed from his deep conviction that the universe must be static and eternal. To force his equations to permit a static solution, he introduced what he called the cosmological constant, a new term that represented a repulsive force inherent in empty space itself. This cosmic repulsion would exactly balance gravitational attraction, allowing the universe to remain stationary for all time. But observations soon rendered Einstein's static universe untenable. In 1929, Edwin Hubble announced that distant galaxies are receding from us. Their light Doppler shifted to longer wavelengths by amounts proportional to their distances. The farther away a galaxy lies, the faster it appears to be moving away from us. This Hubble law provided direct evidence that space itself is expanding, exactly as Friedmann's mathematics had predicted. Faced with this observational evidence, Einstein abandoned his cosmological constant, later calling it the greatest blunder of my life. The universe was indeed dynamic, not static, and general relativity's prediction of cosmic expansion stood triumphant. For decades afterward, cosmologists focused on measuring the rate of expansion and determining whether it would continue forever or eventually reverse into cosmic collapse. The critical question was whether the universe contains enough matter to halt its expansion through gravitational attraction. If the density of matter exceeds a critical threshold, gravity will eventually overcome the expansion, causing the universe to contract back into a big crunch. If the density falls below this threshold, expansion will continue forever, with galaxies drifting apart until stars burn out and the cosmos grows cold and dark. By the 1980s, astronomers had identified a cosmic inventory problem. The visible matter in galaxies, stars, and gas clouds accounted for only about 5% of the critical density needed to close the universe. Even including dark matter, the invisible gravitating material revealed through its effects on galaxy rotation curves and gravitational lensing, the total reached only about 30% of the critical density. This suggested that cosmic expansion should continue forever, gradually slowing as gravity acts as a cosmic brake on the outward motion of galaxies. The rate of deceleration would depend on the total amount of matter in the universe. More matter would produce stronger deceleration, while less matter would allow expansion to coast at nearly constant speed. Measuring this deceleration required observing objects at cosmological distances, where the expansion of space significantly affects the relationship between distance and recession velocity. Type Ia supernovae emerged as ideal cosmic distance indicators because they all reach nearly the same peak brightness, allowing astronomers to determine their distances by comparing apparent brightness to intrinsic luminosity. Two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, began systematic surveys for distant supernova in the 1990s. Their goal was to measure how the expansion rate has changed over cosmic history, expecting to find evidence for gradual deceleration as gravity slows the cosmic expansion. The results defied all expectations. Distant supernovae were consistently fainter than predicted by models of a decelerating universe. The light from these ancient explosions had traveled for billions of years to reach Earth, yet it appeared dimmer than it should if cosmic expansion had been slowing down over that time. Instead, the observations pointed to a universe whose expansion has been accelerating for the past 5 billion years. This acceleration requires a new component of the cosmic energy budget, something that exerts repulsive rather than attractive gravitational effects. Astronomers dubbed this mysterious component dark energy, acknowledging their complete ignorance of its true nature. Dark energy appears to comprise about 70% of the total energy density of the universe, dominating both ordinary matter and dark matter combined. The simplest explanation for dark energy is Einstein's cosmological constant, the same term he introduced to force a static universe, but later abandoned. In this interpretation, empty space itself possesses energy density, creating a uniform repulsive force that grows stronger as the universe expands and creates more empty space. This vacuum energy would be constant throughout space and time, unaffected by the matter and radiation that populate the cosmos. But the cosmological constant faces a severe theoretical problem known as the vacuum energy crisis. Quantum field theory predicts that even empty space should contain enormous amounts of zero-point energy from quantum fluctuations. When physicists calculate the expected magnitude of this vacuum energy, they get a number that is larger than the observed dark energy density by a factor of 10 to the 120th power, making it the worst prediction in the history of physics. This spectacular disagreement between theory and observation suggests that our understanding of vacuum energy is fundamentally flawed. Either quantum field theory's prediction of vacuum energy is incorrect, or some unknown mechanism cancels almost all of this energy, leaving behind only the tiny residue we observe as dark energy. Neither possibility is particularly satisfying from a theoretical perspective. Alternative explanations for dark energy invoke new fields or modifications to general relativity on cosmic scales. Quintessence models propose that dark energy arises from a slowly rolling scalar field, similar to the inflaton field thought to drive cosmic inflation in the early universe. Unlike the cosmological constant, quintessence would evolve over time, potentially leading to observable changes in the acceleration of cosmic expansion. Phantom dark energy represents an even more exotic possibility, with energy density that increases over time rather than remaining constant. This would lead to a big rip scenario where accelerating expansion eventually tears apart galaxies, stars, atoms, and even space-time itself. Current observations cannot definitively rule out phantom dark energy, though most theoretical models favor less catastrophic alternatives. Some physicists have proposed that dark energy might not exist at all, instead arising from modifications to general relativity on cosmic scales. These modified gravity theories attempt to explain cosmic acceleration through changes to Einstein's field equations rather than invoking new forms of energy. However, most such theories struggle to match the precision of general relativity in other contexts while still producing the observed cosmic acceleration. The discovery of cosmic acceleration has profound implications for the future evolution of the universe. If dark energy remains constant or grows stronger over time, the accelerating expansion will continue indefinitely. Galaxies beyond our local group will eventually recede faster than the speed of light, disappearing beyond our cosmic horizon as space expands between us faster than light can travel across the growing gap. This cosmic isolation will leave future astronomers in the far distant future with a very different view of the universe. They will see only the gravitationally bound galaxies in their local neighborhood, surrounded by empty space extending to infinity. The cosmic microwave background radiation, the afterglow of the Big Bang, will be redshifted to undetectably long wavelengths. All evidence for the Big Bang and cosmic expansion will have literally moved beyond the horizon of observability. Dark energy also affects the formation and evolution of cosmic structure. While gravity pulls matter together to form galaxies and galaxy clusters, dark energy works to pull these structures apart. The competition between gravitational attraction and cosmic acceleration determines which structures can form and survive over cosmic time. In regions where dark energy dominates, structure formation shuts down, leaving vast cosmic voids largely empty of galaxies. Current observations suggest that dark energy began dominating the cosmic energy budget about 5 billion years ago, coinciding with the onset of cosmic acceleration. Before this epoch, matter and radiation provided most of the universe's energy density, and cosmic expansion was indeed decelerating as expected. The transition from deceleration to acceleration marks a fundamental phase change in cosmic evolution. Precision measurements of cosmic acceleration have become a major focus of modern cosmology. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and the upcoming Vera Rubin Observatory are mapping millions of galaxies to trace how cosmic expansion has evolved over the past 10 billion years. These surveys use multiple techniques, including supernova observations, baryon acoustic oscillations, and weak gravitational lensing to constrain the properties of dark energy. Space-based missions like the recently launched Euclid telescope and the planned Roman Space Telescope will extend these measurements to even greater precision and cosmic distances. By mapping the three-dimensional distribution of galaxies across cosmic history, these missions aim to determine whether dark energy is truly constant or evolves over time, potentially distinguishing between different theoretical models. The study of cosmic acceleration has also revealed deep connections between cosmology and fundamental physics. Dark energy affects the propagation of gravitational waves over cosmic distances, potentially allowing gravitational wave astronomy to provide independent constraints on cosmic expansion. The interplay between dark energy and dark matter influences the growth of cosmic structure in ways that could reveal the nature of both mysterious components. Some of the most ambitious proposals for understanding dark energy involve probing the quantum nature of spacetime itself. If spacetime has a discrete quantum structure at the Planck scale, this might naturally give rise to an effective cosmological constant through purely geometric effects. The connection between quantum gravity and dark energy represents one of the most profound unsolved problems in theoretical physics. The anthropic principle offers a controversial perspective on the dark energy problem. Some theorists argue that the observed value of dark energy might be selected by the requirement that it allow the formation of galaxies, stars, and ultimately life. In this view, universes with very different dark energy densities would either collapse too quickly or expand too rapidly to form the complex structures necessary for biological evolution. This anthropic reasoning has led to speculation about the multiverse, a vast ensemble of universes with different values of fundamental constants, including dark energy density. Our universe would represent just one member of this cosmic ensemble, selected for observation by the fact that its properties allow observers like ourselves to exist. While intriguing, these ideas remain highly speculative and difficult to test observationally. The mystery of dark energy illustrates how much we still don't understand about the universe's most basic properties. Despite comprising 70% of the cosmic energy budget, dark energy remains completely mysterious. Its discovery has forced cosmologists to confront the possibility that the vast majority of the universe consists of phenomena beyond our current theoretical understanding. Yet this mystery also represents an extraordinary opportunity for discovery. Understanding dark energy will likely require new insights into the nature of spacetime, quantum gravity, or fundamental symmetries of the universe. The solution to the dark energy puzzle may revolutionize physics as profoundly as the discoveries of quantum mechanics and general relativity themselves. The cosmic acceleration driven by dark energy ensures that we live in a universe with a finite window of observability. The evidence for cosmic expansion, the Big Bang, and the large-scale structure of the cosmos will gradually disappear as accelerating expansion carries distant galaxies beyond our horizon. We are privileged to live at a time when the universe reveals its secrets through observations that will be impossible for astronomers in the far future. This perspective adds urgency to our quest to understand dark energy and cosmic acceleration. The universe is providing us with observational clues about its deepest nature, but these clues will not remain accessible forever. The accelerating expansion that dark energy drives is gradually erasing the evidence of cosmic history, making our current epoch a unique time for cosmic discovery and understanding. In the gleaming laboratories of Stanford University, physicists are conducting an experiment that would have seemed like pure science fiction just decades ago. They are attempting to create a bridge between two distant regions of space-time, a traversable wormhole that could potentially allow instantaneous travel across cosmic distances. Using carefully arranged magnetic fields and exotic matter with negative energy density, they hope to weave space-time into configurations that Einstein's equations permit, but nature has never revealed. This audacious experiment represents more than scientific curiosity. It embodies a growing recognition that Einstein's geometric vision of space-time, revolutionary though it was, may itself be just the beginning of an even deeper understanding of reality's fundamental structure. After more than a century of spectacular successes, general relativity faces phenomena that strain its explanatory power and hint at physics beyond Einstein's original conception. The seeds of this revolution lie in the very success of Einstein's theory. Every precision test has confirmed general relativity's predictions with extraordinary accuracy. Yet these same observations have revealed that 95% of the universe consists of dark matter and dark energy, whose nature remains completely mysterious. Either the cosmos is dominated by exotic forms of matter and energy, unlike anything in terrestrial laboratories, or our understanding of gravity itself requires fundamental revision. This puzzle has inspired a new generation of theories that attempt to modify or extend general relativity while preserving its remarkable successes in describing solar system dynamics, gravitational waves, and black hole physics. These theories venture into uncharted theoretical territory, proposing that spacetime might possess additional dimensions, exhibit discrete quantum structure, or emerge from even more fundamental information theoretic principles. Extra-dimensional theories represent one of the most ambitious extensions of Einstein's framework. While we experience space as three-dimensional, modern theories like string theory and Kaluza-Klein models propose that additional spatial dimensions exist beyond our direct perception. These hidden dimensions might be compactified at microscopic scales, curled up so tightly that they remain invisible to ordinary matter and energy. The original Kaluza-Klein theory, developed in the 1920s by Theodore Kaluza and Oscar Klein, demonstrated that general relativity in 5 dimensions naturally incorporates electromagnetism as a geometric property of the extra dimension. This remarkable unification suggested that all fundamental forces might emerge from the geometry of higher dimensional space-time, with different forces corresponding to motion and curvature in different dimensional directions. Modern extra-dimensional models propose that gravity might behave differently at very small or very large scales due to the influence of hidden dimensions. At microscopic distances comparable to the size of the extra dimensions, gravity could become much stronger than Einstein's theory predicts. At cosmic scales, gravitational effects might leak into the extra dimensions, weakening the attractive force and potentially explaining cosmic acceleration without invoking dark energy. Brainworld models envision our three-dimensional space as a membrane, or brain, floating within a higher dimensional bulk, space-time. Ordinary matter and light are confined to the brain, but gravity can propagate through the full higher dimensional space. This scenario could explain why gravity appears so much weaker than other fundamental forces. Gravitational influence spreads throughout the extra dimensions, while electromagnetic and nuclear forces remain concentrated on our three-dimensional brain. Some brain world models predict dramatic deviations from general relativity at cosmic scales. If our three-dimensional space is a brain embedded in five-dimensional spacetime, the expansion history of the universe could differ significantly from standard cosmology. The modified gravitational dynamics might naturally produce cosmic acceleration without requiring dark energy, instead arising from the geometric properties of the higher dimensional embedding space. Massive gravity theories propose a different type of modification to Einstein's framework. While general relativity treats gravitons as massless particles that propagate at the speed of light, massive gravity gives these hypothetical particles a tiny but non-zero mass. This seemingly small change has profound consequences for gravitational physics on cosmic scales. If gravitons have mass, gravitational effects would be suppressed over distances larger than the graviton's Compton wavelength. For graviton masses comparable to the Hubble parameter, this suppression would occur on cosmic scales, potentially explaining both dark energy and dark matter as artifacts of modified gravitational dynamics rather than exotic new forms of matter and energy. However, massive gravity theories face severe theoretical challenges. Most attempts to give gravitons mass lead to mathematical inconsistencies called ghost instabilities, where the theory predicts negative energy, states that would cause vacuum decay. Recent work on ghost-free massive gravity has attempted to resolve these issues, but the resulting theories often exhibit other problematic behaviors at classical scales. Emergent gravity represents perhaps the most radical departure from Einstein's geometric paradigm. Rather than treating space-time as fundamental, these theories propose that space, time, and gravity all emerge from more basic quantum information processing. In this view, the geometric properties of space-time arise from quantum entanglement patterns among microscopic degrees of freedom, similar to how thermodynamic properties like temperature emerge from molecular motion. Eric Verlinder's entropic gravity theory suggests that gravitational force arises from entropy gradients in the quantum information content of space-time. When matter changes position, it alters the information content of different spatial regions, creating entropy differences that manifest as apparent gravitational attraction. This approach attempts to derive Newton's law of gravitation and Einstein's field equations from purely thermodynamic and information theoretic principles. The holographic principle, inspired by black hole thermodynamics, provides another route toward emergent spacetime. This principle asserts that all information contained within a volume of space can be encoded on its boundary surface. Applied to cosmology, holography suggests that our three-dimensional reality might be a projection of information stored on a two-dimensional cosmic boundary. The ADS-CFT correspondence, discovered by Juan Maldacena, provides a concrete mathematical realization of holographic duality. This correspondence establishes an exact equivalence between gravity theories in curved spacetime and quantum field theories without gravity, defined on the boundary of that spacetime. While the correspondence applies to spacetimes with exotic geometries, unlike our observable universe, it demonstrates that gravitational physics can emerge from quantum field theory in the lower dimensions. These holographic insights have led to speculation that spacetime itself might be emergent rather than fundamental. In this picture, the smooth geometry described by general relativity would arise as an effective description of underlying quantum information dynamics. Much as fluid mechanics emerges from molecular kinetic theory, without molecules themselves being smooth or continuous. Quantum error correction has provided unexpected insights into the structure of emergent spacetime. Researchers have discovered that certain quantum error correcting codes have geometric interpretations, with the code structure corresponding to the connectivity of spacetime regions. This connection suggests that spacetime geometry might naturally arise from quantum information systems that protect against local errors while maintaining global coherence. The study of quantum entanglement has revealed deep connections between information theory and spacetime geometry. The amount of entanglement between spatial regions appears to be related to the area of minimal surfaces connecting those regions in higher dimensional spacetime. This relationship, known as the Ryu-Takayanagi correspondence, suggests that quantum entanglement might play a fundamental role in defining space-time geometry. These insights have led to speculation about space-time from entanglement, where the connectivity of space-time emerges from quantum entanglement patterns. In this scenario, regions of space-time that are highly entangled appear geometrically connected, while regions with little entanglement become geometrically separated. The metric structure of space-time would encode information about entanglement patterns in the underlying quantum system. Modified gravity theories like MOND, modified Newtonian dynamics, attempt to explain galactic rotation curves and other dark matter phenomena by modifying the law of gravity rather than invoking invisible matter. MOND proposes that gravitational acceleration behaves differently when it falls below a critical threshold. Becoming stronger than Newton's law predicts at very low accelerations, typical of galaxy outskirts. While MOND successfully explains many galactic phenomena without requiring dark matter, it struggles to account for gravitational lensing observations and the cosmic microwave background patterns that provide strong evidence for dark matter's existence. Relativistic extensions of MOND, such as TeVES theory, attempt to incorporate these ideas into a covariant field theory compatible with general relativity successes. Scalar tensor theories represent another class of modified gravity models that introduce additional fields beyond the metric tensor of general relativity. These theories typically include a scalar field that couples to matter and modifies gravitational dynamics. Depending on the specific form of this coupling, scalar tensor theories can produce cosmic acceleration, explain dark matter phenomena, or both. The chameleon mechanism, developed by Justin Curry and Amanda Weltman, allows scalar fields to exhibit environment-dependent behavior that evades solar system tests while still producing observable effects on cosmic scales. In regions of high matter density, like the solar system, the chameleon field becomes massive and its effects are suppressed. In low-density environments, like cosmic voids, the field becomes light and can significantly modify gravitational dynamics. Galilean theories introduce scalar fields with specific nonlinear self-interactions that preserve a generalization of Galilean invariance. These theories can produce cosmic acceleration while avoiding many of the theoretical problems that plague other scalar field models. The Galilean field can exhibit self-accelerating solutions where cosmic acceleration arises naturally from the field's dynamics rather than requiring fine-tuned initial conditions. Higher derivative gravity theories modify Einstein's equations by including terms involving higher-order derivatives of the metric tensor. These modifications can be motivated by effective field theory considerations or by attempts to renormalize quantum gravity. However, higher derivative terms typically introduce new degrees of freedom that can lead to ghost instabilities unless carefully controlled. The search for alternatives to general relativity has been greatly aided by the discovery of gravitational waves. LIGO and Virgo observations provide new tests of gravitational physics in the strong field, high-velocity regime previously inaccessible to observation. The propagation speed of gravitational waves, their polarization patterns, and the energy loss rates during black hole mergers all provide sensitive probes of modified gravity theories. Precision cosmological observations have also placed stringent constraints on alternatives to general relativity. The cosmic microwave background, supernovae observations, and large-scale structure surveys all probe gravitational physics on cosmic scales. Any successful alternative to general relativity must reproduce the remarkable agreement between standard cosmology and these diverse observational data sets. Despite these constraints, the motivation for seeking alternatives to general relativity remains strong. The dark matter and dark energy problems suggest that either the universe is dominated by exotic physics beyond the standard model of particle physics, or our understanding of gravity itself requires modification. Both possibilities represent profound challenges to our current theoretical framework. The unification of general relativity with quantum mechanics also points toward physics beyond Einstein's original theory. Most approaches to quantum gravity predict modifications to general relativity at extreme scales, whether through discrete spacetime structure, extra dimensions, or emergent geometry. Understanding these modifications might provide clues about observable deviations from classical general relativity. Experimental tests of modified gravity continue to push the boundaries of precision and explore previously inaccessible regimes. Laboratory tests of the inverse square law probe, gravitational physics at submillimeter scales, where extra-dimensional effects might become important. Atomic interferometry experiments test the equivalence principle with unprecedented sensitivity. Pulsar timing arrays search for gravitational wave backgrounds that could reveal modified gravity signatures. Future observations will provide even more stringent tests of alternative gravity theories. Next-generation gravitational wave detectors will probe gravitational physics in extreme environments with exquisite precision. Advanced cosmological surveys will map the large-scale structure of the universe in unprecedented detail. Laboratory experiments will continue pushing toward the fundamental scales where quantum gravitational effects might become observable. The quest for physics beyond Einstein's fabric represents more than theoretical speculation about exotic modifications to well-tested physics. It reflects deep unsolved problems that may require revolutionary new insights to resolve. Whether the solution involves extra dimensions, emergent space-time, modified gravity, or entirely unforeseen physics, the search itself continues to deepen our understanding of the cosmos. Perhaps most remarkably, this search has revealed that Einstein's geometric vision of space-time, revolutionary though it was, might itself be an emergent property of more fundamental information, theoretic or quantum mechanical principles. The fabric of space-time that seems so solid and fundamental to our everyday experience might be woven from threads of pure information, quantum entanglement, and mathematical relationships that we are only beginning to understand. If space-time is indeed emergent rather than fundamental, then Einstein's greatest insights about the geometric nature of gravity represent not the final word on space-time physics, but the first glimpse of an even deeper reality that connects geometry, information, and quantum mechanics in ways that continue to challenge our understanding of the cosmos. This morning, as you woke up and reached for your smartphone, you participated in one of the most remarkable demonstrations of Einstein's curved space-time that occurs billions of times each day around the world. The Global Positioning System satellite that helped navigate your route to work, the atomic clock that precisely timestamps your financial transactions, the gravitational wave detector that monitors cosmic collisions while you sleep, all depend fundamentally on our understanding that we live not in Newton's rigid grid of absolute space and time, but in Einstein's dynamic fabric of curved space-time. Your phone knows its location to within a few meters because engineers have programmed it to account for the fact that time runs differently at different altitudes and speeds. The satellites orbiting 12,400 miles above your head experience time at a rate 38 microseconds per day, faster than clocks on Earth's surface. Without Einstein's relativistic corrections, GPS would accumulate errors of several miles within hours, rendering the system useless for navigation. This is not abstract theoretical physics. This is the fabric of space-time making itself known in the most practical, immediate ways imaginable. Every time you use GPS to find a restaurant, order a rideshare, or track a package delivery, you are relying on humanity's hard-won understanding that gravity is not a force pulling objects together across empty space, but the curvature of space-time itself responding to the presence of matter and energy. The ocean tides that rise and fall along our coastlines twice each day provide another intimate demonstration of space-time curvature. The Moon, 240,000 miles away, creates a gravitational gradient across Earth that stretches our planet slightly in the direction of our satellite. This tidal stretching occurs not because the Moon reaches across space to grab Earth's oceans, but because the Moon's mass curves space-time in such a way that different parts of Earth follow slightly different geodesics through the curved geometry. Even as you sit reading these words, space-time is bending beneath you. Your body's mass, insignificant though it may seem on cosmic scales, creates its own subtle curvature in the fabric of reality. This curvature is far too small to measure with any practical instrument, but it is real nonetheless, a local distortion in space-time geometry that propagates outward at the speed of light, carrying information about your existence to the farthest reaches of the cosmos. The atoms in your body, the chair you sit on, the air you breathe, all follow geodesics through the curved space-time created by Earth's mass. You feel the sensation of weight, not because Earth is pulling you downward, but because you are trying to follow a straight line through curved four-dimensional space-time. The ground pushes back against your feet because solid matter cannot interpenetrate, forcing you to deviate from the geodesic path you would naturally follow in Earth's curved space-time. This perspective transforms our understanding of the most basic experiences. When you drop a ball, it doesn't fall because Earth's gravity pulls it downward. It falls because it follows the straightest possible path through the curved space-time surrounding our planet. The ball's trajectory appears curved to you only because you, standing on Earth's surface, are yourself being accelerated away from a natural geodesic path by the electromagnetic forces that keep your feet from sinking through solid rock. The International Space Station, orbiting 250 miles above your head, demonstrates this principle on a larger scale. The astronauts aboard don't feel weightless because they are beyond Earth's gravitational influence. They feel weightless because they are in free fall, following a geodesic path through Earth's curved space-time. Their orbital velocity ensures that this geodesic curves around Earth rather than intersecting its surface, creating the illusion of floating in a zero-gravity environment. But space-time's influence on our daily lives extends far beyond navigation and orbital mechanics. The light from your smartphone screen, the radio waves carrying your cellular communications, the wireless signals connecting your devices to the internet, all follow geodesic paths through curved space-time. The curvature is so slight near Earth's surface that these paths appear perfectly straight to our limited perception, but sensitive instruments can measure the tiny deflections that general relativity predicts. The very atoms that compose your body bear witness to space-time curvature. The precise energy levels of electrons orbiting atomic nuclei depend subtly on gravitational effects, creating spectroscopic signatures that atomic clocks use to maintain extraordinary precision. The cesium fountain clocks that define international time standards must account for gravitational frequency shifts as small as a few parts in 10 to the 18th power. Modern banking and financial systems depend on this precision timekeeping to synchronize transactions across global networks. High-frequency trading algorithms rely on timestamps accurate to microseconds, requiring clock synchronization protocols that incorporate relativistic corrections. The blockchain technologies underlying cryptocurrencies use cryptographic hash functions that depend on precise time ordering, making Einstein's space-time curvature an essential component of 21st century digital infrastructure. Weather forecasting systems use gravitational models to track the motion of air masses through Earth's gravitational field. Meteorologists must account for how pressure gradients and temperature differences interact with gravitational acceleration to predict storm formation and atmospheric circulation patterns. Even seemingly simple phenomena like the formation of raindrops involve the interplay between electromagnetic forces, surface tension, and gravitational acceleration through curved space-time. The construction of large buildings and bridges requires engineers to account for gravitational variations across their structures. The slight difference in gravitational acceleration between the top and bottom of a skyscraper affects the building's structural dynamics and must be incorporated into earthquake safety calculations. Precision surveying for major infrastructure projects uses gravitational measurements to map subsurface geology and detect underground cavities or mineral deposits. Satellite communications networks must continuously adjust for relativistic effects to maintain signal coherence across continental distances. The Doppler shifts caused by satellite motion, combined with gravitational redshift effects from Earth's curvature of spacetime, require sophisticated frequency correction algorithms. Without these corrections, satellite internet, television broadcasts, and military communications would suffer from significant signal degradation. Medical imaging technologies like MRI scanners rely on precisely controlled magnetic fields to manipulate atomic nuclei in human tissue. The quantum mechanical behavior of these nuclei is subtly influenced by gravitational effects, particularly in high-precision measurements. Some proposed medical applications of atomic interferometry would use gravitational sensors to detect density variations in human tissue with unprecedented sensitivity. The global positioning system has enabled precision agriculture applications that depend on centimeter-level accuracy for automated tractors and harvesting equipment. This precision requires real-time correction of GPS signals using ground-based reference stations that account for atmospheric effects, satellite clock errors, and relativistic corrections. The resulting systems can plant seeds, apply fertilizers, and harvest crops with a precision that maximizes yield while minimizing environmental impact. Emergency response systems use GPS-enabled devices to locate accident victims, coordinate rescue operations, and guide first responders to precise locations. The life-saving potential of these systems depends entirely on the relativistic corrections that Einstein's theory makes possible. In disaster scenarios where every minute counts, the difference between accurate and inaccurate positioning can literally mean the difference between life and death. Scientific research across virtually every discipline now depends on precision measurements that require relativistic corrections. Particle accelerators like the Large Hadron Collider must account for gravitational effects on particle beams traveling at near light speeds. Astronomical observatories use atomic clocks to coordinate observations across global networks, enabling interferometric techniques that resolve details smaller than could be achieved by any single telescope. The detection of gravitational waves has opened an entirely new window on the universe, allowing us to observe cosmic events that are invisible to traditional telescopes. These ripples in space-time carry information about black hole mergers, neutron-star collisions, and potentially the quantum fluctuations that seeded cosmic structure formation in the early universe. Future gravitational wave observatories will monitor space-time disturbances as small as 1/10,000th the width of a proton. But perhaps the most profound implication of living in Einstein's fabric is philosophical rather than practical. Our understanding of space-time curvature fundamentally changes how we think about our place in the cosmos. We are not separate observers watching the universe unfold from some external vantage point. We are integral participants in the cosmic dance between matter, energy, and space-time geometry. Every movement we make, every breath we take, every thought we think, occurs within and influences the fabric of space-time itself. The distinction between observer and observed between mind and matter, between self and cosmos, becomes blurred when we recognize that consciousness itself emerges from quantum processes occurring within curved space-time. We are not separate from the universe observing it from outside. We are the universe becoming aware of itself from within. This perspective reveals the deep interconnectedness of all existence. The carbon atoms in your body were forged in the cores of dying stars, compressed by gravitational forces so intense that they fused lighter elements into heavier ones through nuclear reactions powered by space-time curvature. The calcium in your bones, the iron in your blood, the oxygen you breathe, all bear the signatures of cosmic processes driven by the interplay between matter and space-time geometry. The water molecules flowing through your bloodstream have journeyed across billions of years of cosmic history, from the primordial hydrogen and oxygen created in the first minutes after the Big Bang, through countless cycles of stellar formation and destruction, to arrive finally at this moment in your living body. Each molecule carries within its quantum structure the accumulated history of gravitational interactions across cosmic time. Your DNA, the molecular blueprint that guides your biological development, represents an information processing system that has evolved over billions of years within Earth's curved space-time environment. The precise chemical bonds that store and transmit genetic information depend on quantum mechanical processes that are subtly influenced by gravitational effects. Life itself is a space-time phenomenon, an emergent property of matter and energy organizing itself within the curved geometry of Einstein's cosmos. The neural networks in your brain that give rise to consciousness operate through electrochemical processes that propagate information at speeds much slower than light. Yet these processes somehow give rise to subjective experiences that feel immediate and unified. The relationship between physical brain states and conscious experience remains one of the deepest mysteries in science, but it clearly occurs within and depends upon the fabric of space-time that Einstein revealed. Human civilization represents a remarkable phase transition in the universe's evolution. The emergence of self-aware information processing systems capable of understanding their own cosmic context. Through science, mathematics, and technology, we have developed the ability to perceive and manipulate space-time curvature, to detect gravitational waves from cosmic collisions, to navigate using relativistic corrections, and to contemplate our own existence within the fabric of reality itself. This achievement becomes even more remarkable when we consider the scales involved. Human beings, composed of roughly 10 to the 28th atoms, exist at intermediate scales between the quantum realm of individual particles and the cosmic realm of galaxies and dark energy. Yet from this intermediate vantage point, we have managed to understand phenomena spanning more than 60 orders of magnitude in size and time, from quantum fluctuations lasting billionths of a second to cosmic evolution over billions of years. The fact that the universe has evolved conscious observers capable of understanding space-time curvature suggests deep connections between the physical laws that govern cosmic evolution and the information processing capabilities required for intelligence. The anthropic principle points toward the possibility that fundamental constants like the strength of gravity and the speed of light are fine-tuned to allow the emergence of complexity and consciousness. Whether this fine-tuning reflects selection effects in a multiverse of cosmic possibilities, fundamental principles yet to be discovered, or simply remarkable cosmic coincidence, the result is undeniable. We live in a universe where space-time curvature allows the formation of stars, planets, molecules, cells, and ultimately conscious beings capable of contemplating their own existence within Einstein's fabric. This brings us to perhaps the most profound realization of all. We are not merely living in space-time, we are expressions of space-time's capacity for self-organization and self-awareness. The curved geometry that guides the motion of planets and the propagation of light also enables the complex chemistry of life and the neural processes that give rise to consciousness. We are the universe awakening to itself, space-time becoming aware of its own curvature. The children being born today will grow up in a world where gravitational wave astronomy is routine, where quantum computers exploit space-time geometry for information processing, where precision atomic clocks reveal new physics at the intersection of gravity and quantum mechanics. They will take for granted technologies that depend fundamentally on our understanding of curved space-time, just as we take for granted technologies that depend on electromagnetism and quantum mechanics. But more than technological capabilities, these children will inherit a worldview transformed by Einstein's insights about the nature of space, time, and gravity. They will understand intuitively that they live not in Newton's clockwork universe of separate objects moving through empty space, but in Einstein's dynamic cosmos, where matter, energy, space, and time are woven together into a single, coherent fabric. This understanding carries with it both humility and wonder. Humility because it reveals how much we still don't understand about the deepest nature of reality. Dark matter and dark energy remain mysterious despite comprising 95% of the universe. The unification of general relativity with quantum mechanics continues to elude our best theoretical efforts. The origin of space-time itself in the quantum fluctuations of the early universe pushes the boundaries of both observation and imagination. But also wonder, because Einstein's geometric vision has revealed the cosmos to be far stranger and more beautiful than our ancestors ever imagined. We live in a universe where space and time form a unified fabric that can bend, stretch, ripple, and sing with gravitational waves from cosmic collisions billions of light years away. We inhabit a reality where the distinction between matter and geometry dissolves into a deeper unity described by mathematical equations of breathtaking elegance and power. As you close this exploration of gravity and space-time, as you return to the ordinary activities of daily life, remember that you carry with you a secret knowledge that transforms even the most mundane experiences. When you feel your feet firmly planted on the ground, you know that you are being accelerated away from a natural geodesic path by electromagnetic forces. When you watch the sunset behind the horizon, you know that the light reaching your eyes has followed a geodesic path through the curved space-time surrounding our star. When you check the time on your phone, you participate in a global network of atomic clocks that maintains synchronization by accounting for gravitational time dilation. When you use GPS to navigate, you rely on relativistic corrections that prove, millions of times each day, that we live in Einstein's curved space-time rather than Newton's absolute space and time. You are not floating in space, isolated and alone in an indifferent cosmos. You are woven into the very fabric of reality itself, connected through space-time curvature to every star, every galaxy, every quantum fluctuation that has ever existed or ever will exist. Your thoughts and actions ripple outward through curved space-time, carrying information about your existence to the farthest reaches of the universe at the speed of light. This is Einstein's ultimate gift to human understanding. The recognition that we are not separate from the cosmos, but integral to it, not observers of space-time, but participants in its eternal dance of matter, energy, and geometry. We live within the fabric of reality itself, and in understanding that fabric, we come to understand something profound about the nature of our own existence within the magnificent, mysterious, ever-expanding universe that is our cosmic home.